Okay, we are starting. Hello, am I audible?
Yes.
Yes,
Okay,
sir.
so Vidya is there with us.
Yes, sir.
Vidya. So let's
Yes,
first
sir.
introduce the speaker to all the attendees, all the participants. Then we'll be starting. Okay, Kalita.
Yes, sir.
So I'm leaving it to Vidya. Okay, it's over to Vidya.
Yes. Good morning, good afternoon, everyone. Sorry. Welcome to the second day of webinar on emerging technologies in biofuel production 2020, organized by the Department of Mechanical Engineering, Assam Engineering College, in association with Assam Science and Technology University under TEQIP III. Today, we have one of our renowned scientists of Assam, Dr. Pankaj Kalita, sir. He's here to show us some light on integration of emerging technologies for clean power generation. Dr. Kalita has graduated from Jorhat Engineering College and completed his master's and PhD in energy from IIT Guwahati. Starting his professional career from Tezpur University, he now has 7 years of teaching and 16 years of research experience in the field of renewable energy, currently serving as assistant professor in the Center for Energy in IIT Guwahati. Dr. Kalita is a recipient of India Distinguished Visiting Fellow awarded by University of Nottingham, United Kingdom in 2010, attended the prestigious India-UK Young Scientist Networking Conference on Low Carbon Technologies. He has published 37 peer-reviewed research papers in various reputed journals, contributed to many book chapters, and has more than 20 national and international conference papers. His current areas of interest includes solar energy conversion, energy management, energy storage, and integration of renewable energy for remote electrification. We are glad to have you among us, sir. Now I request Dr. Kalita, sir, to share his valuable words. The platform is yours now, sir. You can share it.
Thank you very much, Birisha, for a nice introduction. And I also like to thank Dr. Prasanta Kumar Chaudhary for giving me an opportunity to speak to this august audience. So let me first share my presentation. So I hope that my slides are visible to you all.
Yes, sir, it is
visible.
Okay, it's fine. Fine, Kalita.
Yeah. So without delay, I should start my presentation. As Birisha rightly said, I'll be speaking about emerging integration of emerging technologies for clean power generation. So we'll have different component of renewable energy technologies, and we are integrating those technologies for generating clean power. So before we touch our actual work, what we are proposing to be discussed in this class, let us give some kind of background why this biomass energy is quite popular, and then what are the scopes or the way we can think forward. So in the introduction, I have some slides about energy scenarios, and then how this renewable energy contribution is increasing with time, and what is the need of this kind of renewable energy technologies. So in the first figure, it shows the contribution of energy generation. So China is producing huge, and then at the same time, we can say it's a carbon dioxide emission. So in the horizontal axis, it shows share of carbon dioxide emission, and in the vertical axis, it shows the countries. So as you can see very clearly, this China is producing about 27.121% of global carbon dioxide emission, followed by US, which is 14.58, and India is about 6.82. So in global energy scenario, India is a third highest producer of carbon dioxide, which is already, I have said, it is 6.82. And this energy generation contribution, what is we're enjoying today, it's about 90% carbon dioxide is comes globally. Okay, so these are mostly this coal-based power plants, so it emits a huge amount of carbon dioxide. So this figure is, I hope all are familiar with this figure. So here what it shows the percentage of carbon dioxide in the Earth atmosphere As you can see, in 1859, the emission level in the Earth atmosphere is about 300 and close to 300. Okay, and then it increases sharply with times. And if you see 2018, it crosses 400 ppm. As you are aware that this safe limit of carbon dioxide in the Earth atmosphere is about 350 ppm. So already we are in a very dangerous state. So we can take a comparison in 2019 and 2020. So in 2019, this carbon dioxide concentration in the Earth atmosphere was 414.71 ppm. And if you see just 1 year after, it is June 4, 2020. So you can see it's a 416.57. So it's a rise in 2 ppm of carbon dioxide emission. And we can see the result of this increase in carbon dioxide in the Earth atmosphere, which lead to increase in Earth atmospheric temperature. And finally, what we can see, there are adverse effects like sudden climatic change of something like very harsh weather and cyclones. And we can see the polar bear there, where ice melts, and then that's a big concern of the environmentalists. So in order to save our planet, we need to rely on renewable energy sources, which can emit lesser amount of carbon dioxide compared to coal-based power plant. So here it shows the percentage of energy which is contributed to the global demand in case of fossil fuel. In case of fossil fuel, it is 73.8%, okay, which is the contribution for power generation, and for renewable energy, it is 26.2%. Again, if we classify this renewable energy to different categories like hydropower, which includes non-renewable and renewable. As you know, if a hydropower power plant is having capacity more than 25 megawatt, it is called non-renewable. If it is less than 25 megawatt, it is called renewable. When we say in this kind of comparison, it includes both renewable and non-renewable hydroelectric power plants. Okay, so total contribution is about 15.8%, followed by 5.5% wind power, 2.4% solar PV, and 2.2% bioenergy, and very small amount of geothermal, then concentrated solar power and ocean powers are there. Again, if we see the second figure, what it's shown here is the renewable energy generation. So worldwide, about 1,246 gigawatt of energy contribution is coming from renewable energy sector. Out of that, 404 gigawatt energy is generated by China, followed by European Union, which is 339. So if we draw a line here at 200 gigawatt scale, and then we magnify it, then what we can see? So we can see this kind of figure, where what we can see, United States is producing about 180 gigawatt of energy from renewables. So this yellow color is solar PV, and then this green color is biopower, and then blue color is wind power, and small amount of power is here in the orange color. And in Germany, they produced about 113 gigawatt of energy, and India is about 78, and followed by Japan 64, then United Kingdom is 42. Okay, so from these two plots, what we can summarize that the continuous growth in renewable energy, that is overall share of 33% to meet increasing energy demand has been observed, and 26.2% of renewable electricity achieved with overall installed capacity. And this bulk share of renewable electricity is from hydropower, followed by wind and solar, what we can see here. So it's hydropower, then wind, then we have solar. And also we have seen China is this one, what you can see, China is among the leading countries of power generation from renewable energy. So now let us learn the energy mix of India. So here, out of total energy, about 54% energy is contributed from coal, followed by renewable, which is 35%, close to 35%. Then we have gas, then nuclear, lignite, and diesel. Okay, so if we again magnify this renewable energy part, then large hydro contribution is about 12.6%. Then the wind power is 10%, and solar is 8.7%. Even though solar is I think in 2 years time again we'll get different figures of the solar, because government has a ambitious plan to increase the power generation facility. Of course, wind is also included in that target. And biomass is about 2.7, and small hydro is 1.3, and waste to energy is very less, about 0.04. So this India's energy consumption would grow by 4.2% per annum, which is faster than all the major economies in the world. So this figure shows the share in primary energy consumption in 2035. So this is some kind of predicted models. So as per the predicted models, it is said that about 9% rise will be there, share from Indian context. Okay, and this coal will remain the dominant fuel produced in India, with a 65% share of total production in 2035. That is the result of predicted model. And then renewable overtake oil as the second largest, and increasing from 4 to 14% in 2035, as oil drops from 10% today to 3% by 2035. So that's the predicted model. People have already done a lot of investigation, and finally it is found that it should be something like that. Of course, it is not something like it will be absolutely 9%. It may vary plus minus 2-3%. Now let us see the uses of renewable energy in different commercial sectors. So here what happens in the core of this diagram, if we consider the core cylinder, here what happens, this part is heat and other direct uses, which is about 59%. Then power generation is 35%, and 5% is transportation. Again, we can break it like how these will be utilized, like biomass heat industry, which takes 24%. Then direct heating of buildings, which is 30%. And then we'll have geothermal heat, which is less than 1%, okay? And then solar thermal heat, which is 5%. And as far as transportation fuel is concerned, we will mostly rely on biofuel plants. And then for power generation, we'll have power generation, biomass power 3%, hydro 7%, wind 14%, solar 11%, then concentrated solar power 1%, then geothermal is less than 1%. And also, you are aware about the target of government for renewable energy sectors. So by 2022, they have a plan to install about 175 gigawatt power energy generation unit. So if we classify it from where this energy will come, so 5 gigawatt is expected to come from solar hydro, small hydro, and 10 gigawatt will come from biomass, then 40 gigawatt will from rooftop solar, then 60 gigawatt again solar photovoltaics, and then 60 gigawatt will come from wind energy. So this is the distribution of energy from where no contribution of 175 will meet. As also you are aware now, like India is the third largest producer of electricity, and according to India's renewable energy target by 2020, a total of 175 gigawatt energy to be produced from renewable energy sources. Okay, so we'll just have a look about the biomass potential, because mostly we'll be concentrating today on biomass energy conversion. So here, so darker the color is, the higher is the potential. So here it says is a high potential, but no, I have to, what I think northeastern region needs to be recoloring. So because as we understand, we have huge amount of biomass potential. So, so of course, this is taken from this source, indian.um.dk. Okay, so here darker color indicates more than 3000 megawatt electricity, followed by lighter colors, 2001 to 3000, then 2001 to 2000, then 501 to 1000, and so on. Okay, so what is the potential? So as per the predicted model, it is found that India has the potential of about 18 gigawatt of energy from biomass. And if we classify again from where this 80 gigawatt will come, so we can see here. So this is from grid interactive solar power, or sorry, grid interactive power, which is capacity in megawatt, which is given here. And then we'll have off-grid or captive power, okay, also capacity in megawatt. So if we see the total energy generation from biomass is about 6,000 megawatt, and out of that, about 5,000 megawatt energy is coming from this grid interactive power, okay. And when we say this biomass power, it includes combustion, gasification, then cogeneration by using bagasse, then waste to energy like thermochemical and biochemical conversion. And here also in the off-grid, what you can see here, there are applications in rural and industrial, and waste to energy is also included. Okay, so that's how what we can say about 83% of present energy produced from biomass are grid connected, while 17% is off-grid connected. Okay. Now let us come to our today's topic, how we are integrating this technology. So in this slide shows the different components, how we are integrating. Okay, then we'll study one by one. So this is a biomass gasifier of capacity 10 kilowatt. And what you can see, we'll study the different components and how it works and what are different stages and processes. So just to give an idea how this kind of system operates, I'll just give this information. Okay. So this gas is generated here. This gas, what is generated, is composed of carbon monoxide and hydrogen primarily. Of course, small amount of methane is present. So that's how this gas is burned here in the what is called observing tube. So once we are confirmed that gas is generated, then we can supply the gas to the engine. So these are the control panel. We can see the temperature at different position, and all the components I'll be showing. So this video will give some information and then how this is burning there. And then we'll have anaerobic digestion system here. So this is the inlet tank, this is a fermentation chamber, and we'll have this what is called outlet tank. And then gas is generated here, and then this is collected with the help of this balloon, and then we can burn it here for gas generation. And he's a Sairam, he is one of the PhD students. His work is on this biogas technology, and then he's trying to do something internally, how to enhance the production of biogas. And then we'll have this engine setup. This engine is a variable compression ratio engine, and it's a very costly engine. It's about 15 lakhs we have procured. Here what we can do, we can sense the compression ratios. Otherwise what happens, we can buy a low-cost engine having fixed compression ratio. So the purpose of buying this machine is to not machine, this engine, is to optimize the compression ratio, means at which compression ratio will get the best emission performance, best engine performance, and best combustion performance. So this is the purpose why this kind of engine is required. And then we need to mix these two gas to introduce in the engine. So that's a challenging task. So we have developed one what is called connector through which you can inject these gases at a proportionate level without disturbing the engine performance. And the downstream, because as you know, this exhaust of the engine is always excited at a very high temperature. So this can be utilized for different applications. So we have done 3 applications. One is for drying, and then second one is for refrigeration, and third one is for distillation. So this is complete integration of renewable energy technology package for rural electrification and utility. So now we'll study one by one. So these temperature ranges are also shown here, so that we can think at what temperature which technology can be utilized. So this is the schematic of that plant. So we'll have this reactor, which is a downdraft biomass gasifier, and then we'll have some cyclone separators first, and then cooling and tar removal, and then we'll have blower, again cooling, again we have what is called cyclone separator for separate those heavy particles, and then what we'll get finally is the gas, which is a clean gas, and by holding a flame we can see the gas is generated or not inside the hopper. inside the what is called reactor. And then once it is confirmed, then what we'll do is just close this valve, and then no gas is supplied through this sawdust filter and then fabric filter and then storage, and then this will be connected to the engine. Of course, while before introducing to the engine, we this is to go through this Venturi type mixing chamber, which is very, very critical. So we faced a lot of difficulty in designing this, but finally we have designed it, and then we have submitted this article in one of the journal publications. So first review is gone. I think it will publish soon. And then this is an anaerobic digestion. So what we have done in a nutshell, we're trying to enhance the activity of the microorganisms here. And as you know already, those who are working or those who know about biogas digester, so with time there is a accumulation of scum on the top of this. That means that the interface between the solid and gas, because gas is generated at the top, and it forces from the top and it goes down and is move up. Okay, so at the interface the scum formation is observed. So because of that we have arranged one passive sterilization technique, so you can stir it and you can break the scum. And also inside this field digester we have incorporated thermocouples, and these are connected to data equation system. So as you know, these microorganisms are very, very sensitive to the temperature. So what we are trying to achieve here, we are trying to control the temperature at 35 degrees C. Okay, so because at 35 degrees C, this mesophilic microorganisms work best, and then it is expected to get more biogas production. And how we are doing this? We are doing by using solar photovoltaic and solar thermal technology. So we need a pump to circulate the fluid here, and then that fluid temperature fluid will get from this evacuated tube solar collectors, and that is introduced through this pumping system, and then it controls. And this power required to run this DC pump is taken from the solar PV. And this is the engine. This is the dual fuel. This is dual fuel, but it's a variable compression ratio engine. So all the control and other things are there. So we can calculate all the thermodynamic parameters as well as combustion, emission, and then performance of the engine at different conditions. Now, the few slides I'll tell about general thing. Then again, we'll come back to the our theme. Like biofuel, we talk about bioenergy and its conversion. So there are different routes, like thermochemical conversion and biochemical conversion. So under thermochemical conversions, we'll have combustion, gasification, and then pyrolysis. So in combustion, what we do normally, we just burn the fuel and then we generate steam, and that steam is expanded in a turbine and we can generate energy out of it. Okay. Sometimes we can use that steam for other applications, maybe in process industries. So steam is required at isothermal condition, that can also be done. In gasification, what happens? So we are not providing sufficient oxygen for complete combustion. So our target is to get carbon monoxide in the product side and hydrogen in the product side. Okay. So once we have this composition, so we can use this fuel as a fuel for gas turbine. Okay. So once we generate this energy, that can be expanded in a gas turbine and it can generate electricity. Okay. And if we have generated significant amount of hydrogen, and we have the technology to separate the hydrogen from the mixture of carbon dioxide, carbon monoxide, and other element present in the producer gas, then we can think of utilizing a fuel cell for electricity generation. So that's how this fuel cell has come here. And in case of pyrolysis, as you know, there are many products of pyrolysis. So it may be categorized as gaseous product, then oil, and then charcoal. Once we generate this gas, again we can combust it in the gas turbine and we can generate energy. And oil, what we generate, that can be upgraded, and once we get the upgraded fuel, that can be used in diesel engine and we can generate energy, and that may be a fuel. Okay, that's why each position is here. And we can generate charcoal, which is a product of pyrolysis, and that is nothing but a fuel, because charcoal can be used as a fuel for energy generation. And as far as biochemical conversion is concerned, there are routes like digestion and fermentation. In the digestion, we can generate biogas, what we have explained just now, and we can know once we clean it, because biogas composed of methane and carbon dioxide and a small percentage of hydrogen sulfide. If we purify this carbon dioxide and hydrogen sulfide, then what we will get is a methane, pure methane, which is resemble like natural gas. So once we have that kind of gas, then we can burn it in a gas engine and we can generate electricity out of it. So this kind of facility already we have grown, and this has been disseminated to one of the place nearby IIT Guwahati. So that's Auniati Hotro. If somebody interested, then they can come and see there. So how the way we have installed that kind of system for generation of electricity. Of course, we are not telling or discussing about fermentation today, and extraction is something like, if you have biodiesel switch and all, we can do transesterification, then we can produce biodiesel, and that can be used as fuel. So today we'll be discussing mostly about thermochemical conversion routes, and then we'll have biochemical, that too on digestion. So without delay, let us discuss about biomass conversion, basically what is called gasification. So this conversion of solid fuel to gaseous fuel. Okay, so we will have solid, and then we are converting to gaseous fuel. Then produce combustible gas mixture. These gas mixtures are nothing but carbon monoxide, then hydrogen, and methane. Already I have explained it. And it involves partial combustion of biomass. I will give an example what is partial combustion and what is complete combustion or stoichiometric combustion. So in case of this biomass gasifications, there are 4 distinct processes. These are called drying, pyrolysis, combustion, and reduction. And in case of this gasification process, we need to maintain the equivalence ratio is equal to 0.2 to 0.4. We know how to define this equivalence ratio. Okay, if we know fuel to air ratio of actual and fuel to air ratio of stoichiometric equations, then from that we can calculate what is the equivalence ratio. And for example, as I said, if I consider a fuel, say methane, so 1 mole of methane reacts with 2 mole of oxygen. It gives 1 mole of carbon dioxide and 2 mole of H2O. Okay, so here what happens, we have provided sufficient amount of oxygen for complete combustion. That's why in the product side, no fuel is present, only carbon dioxide H2 is present. So if our combustion is complete, then what we will get, carbon dioxide and H2 is expected at the product side. And in case of partial oxidation, so methane reacts with half of the oxygen, what we will get, carbon monoxide plus 2H2, right? So here what happens, we are not getting carbon dioxide, we are getting carbon monoxide and hydrogen. So these 2 elements are required in case of gasification. So as I said, it has 4 distinct zones. If we come from the top of the gasifier, it's a drying zone, then we have pyrolysis, then combustion, reduction, then ash removal. Okay, so ash is collected from the top, air is introduced in the next section, and biomass is fed from the top. Okay, and gas is collected from the just above the what is called ground plate. Okay, so here ash is accumulated and that can be collected. So this reactor assembly, you can think of something like this. So we can introduce fuel, okay, like biomass, coal, everything, whatever we have, and then we can introduce H2O or maybe oxygen or maybe air. So if we are interested to maximize the calorific value of the gas which is generated from the biomass gasification system, then of course we will go for steam or oxygen, not air, because as you know, air is a composed of nitrogen and oxygen. Okay, so that we can decide which kind of oxidizer we can use for a particular set of operation. And finally, what we'll get at the end is this kind of gases. Okay, carbon monoxide, carbon dioxide, hydrogen, methane, H2O, C2 plus tar. Okay, so tar is one of the major problems. So it depends the kind of technology used, and this is actually one of the key or active research. So someone interested to do, interested may carry out this kind of work on tar removal. So here, these are the chemical reaction takes place in this reactor. So first, oxidation reaction. This is carbon reacts with H2O. Carbon reacts with oxygen. It produces carbon monoxide, and heat formation will be there. And then partial oxidation reaction, hydrogen reacts with oxygen, it will produce H2O. In bordered reactions, carbon reacts with carbon dioxide, it produces carbon monoxide. Then water gas reaction, carbon reacts with water vapor, it produces carbon monoxide and hydrogen. And then water sieve reaction, this carbon dioxide reacts with hydrogen, it produces carbon monoxide and H2O. And finally, in methane production reaction, this carbon reacts with H2, it will convert to CH4 plus 75 megajoule per kilomole of per kilomole. Okay, so these reactions can be accelerated by using some kind of catalyst, and that has to be done at very high temperature and high pressure. Okay, if we are really interested about methane production, then we should think of a very high temperature and high pressure application. So as far as classification of biomass gasifiers are concerned, or say gasifiers are concerned, there are many classifications. These are based on interaction of gasifying agent and solid fuels. So it may be fixed bed, maybe fluidized bed, maybe entrained bed. Again, this fixed bed can be classified into 3 groups, like updraft, downdraft, and crossdraft, and these are classified based on the relative direction of flow of gasifying agent. In case of fluidized bed gasifiers, we can classify into 2 categories: bubbling fluidized bed and circulating fluidized bed. If only solids will percolate on the air when it's supplied from the bottom, that's called bubbling. If that solid particle circulates in a closed loop, that is called circulating fluidized bed. So of course, velocity of circulating fluidized bed will be higher compared to bubbling bed. So this velocity is one of the classifying variable for this kind of gasifiers. So there are operational issues in case of fixed bed gasifiers, like slagging and non-agglomeration, and syngas exit blockage, then slag mobility issues, and refractory degradation. So with time, refractory degrades in this kind of arrangement. And in case of fluidized bed, this blade agglomeration and fluidization is an issue, and S deposition and fouling is one of the major issues. And in case of entrained bed, which is very, very big in size, so slag mobility is an issue, refractory degradation, and syngas cooler fouling and plugging are issues. So this has to be addressed while making this kind of arrangement. So also these processes already we are aware about the different processes of gasification. So drying, pyrolysis, combustion, and reduction. And we can see at what temperature this is taking place. Up to 200 degrees, this drying will take place. Then up to 600, this pyrolysis will take place. Then 700 to 1000, it's a combustion will take place, and then reduction will take place, and 800 degrees. Okay, but this depends on the fuel. So what kind of fuel we are using? So normally, to get this kind of information, we need to do TGA analysis, which is nothing but thermogravimetric analysis. So once we know the degradation pattern with time and temperature, then from that we can conclude at what temperature these things are happening. Okay, that we can think of designing a new reactor as well. So since we are dealing with a fixed bed type gasifier, so just to explain how it works and then what are different components. In the top portion, it's a drying zone where feedstock is added, followed by pyrolysis, combustion, and reduction. So these are the next sections, and air is introduced in the next section. Normally, what happens in the bigger unit, we need some kind of arrangement for supplying air. So we need blower and other things. But in a lower capacity, we don't need that kind of devices. So it's designed in such a way that if we make 2 limbs here, and if we ignite it, there is a sucking effect. So if engine is on, and then if we hold the flame here at this position, then what will happen? There is a sucking effect. Due to this sucking effect, this bed, normally in this bed, coal is present. So this coal will burn first, and this heat transfer will take place from this coal to this biomass. And then slowly what happens, initially moisture will be removed, that's called drying zone. Then pyrolysis will take place, there's combustion already taken place. And then finally what we have is a reduction zone. So all the things should be collected here, and then this will fall to this S pit. Okay, S can be collected, and the gas generated here. So will be channelized to this periphery, and this will move to the engine. And before it will move to the engine, of course, it has to pass through this cleaning and cooling system. Okay, so these are the temperature. Normally, we have these facilities to monitor the temperature at different levels of this gasifier system. So this gasifier is applied in our experiments, and it's a 10 kilowatt capacity biomass gasifier, and biomass consumption is about 10 to 15 kg per hour. So wood logs are used, and conversion efficiency is 70 to 75, and producer gas flow rate is about 7.5 kg per hour, and calorific value of the gas is found to be 5800 kilojoule per cubic meter. And density of the woodlog is about 1287 kg per cubic meter. And feedstock, what we have taken, that's properties are also given here. So this is the reactor system, and this is the cooling system, and we'll have this is a small blower. It blows air, blows producer gas, and before it goes to the engine. So this is the what is called cleaning system, and it stores here, and then finally from there it goes to the engine system. So normally what we can say, so this pre-treatment of feedstock is very, very important to maximize the performance of this gasifier. And then we need to have reactor. This is called gasifier. We can supply steam. In order to supply steam, we need a boiler, and then as extraction will be there, we can collect the S. And then this blue colored box is nothing but cleaning system. So it's a energy intensive, and critical thoughts are required for cleaning the gas, because if more or impure gas introduced in the engine may damage. Okay, so proper care has to be taken in this section, and then finally it will go to the engine. Sometimes these gases are used in gas turbine also. So for gas turbine, it is very, very sensitive to this particulate matter. We'll be discussing in the next slide. And then cleaning and complete removal of particulate material, and that is essential for internal combustion engine application. And for spark ignition engine, it can operate with producer gas alone. For CI engine, it operates in dual fuel mode. Okay, and for India, so following capacities are available. Like thermal, it's about 60,000 to 21,000 into 10 to the power cube kilojoule per hour. That's the available capacities. And electrical goes from 4 to 1100 kilowatt electrical. Okay, that kind of systems are already in practice in India. So as I said, the impurities and their tolerance level. So impurities, if we consider the stars, alkali metals, then N species means NOx, SOx, and sulfur, S species means sulfur and halides. So it has got different what is called ranges, and then we have this. So if you compare IC engine, it's value, if we take the scale micron, so it should be 10 micron for particulates, and for tar it should be less than 100 milligram per nm cube, and alkali metal is 0.1 less than 0.1 milligram per nm cube. N species are not required in case of IC engine, and S species is less than, that should be less than 20 ppm. Okay, so similarly for gas turbine, then molten carbonate fuel cells and the solid oxide fuel cells, there are some ranges that has to be followed, otherwise it will be damaged. It will be damaging the system what we are going to use it. And as far as tar and particulate level of gasifiers are concerned, these are also sensitive. So for fixed bed gasifiers like updraft, downdraft gasifiers, so this particulate loading should be less than 10, okay, gram per nm cube, and here in tar content should be less than 6 gram per nm cube. So that way, these ranges are people have done experiments, and they have listed this range, so it should not be more than the range provided by the researcher. So let us take a very small example about this running of a biomass gasifier. So if biomass gasifier is used to run a CI engine, the engine operates in the dual fuel mode with 80% diesel replacement. The gasifier engine system produces 350 kilowatt of power, and calculate the biomass feeding rate to the gasifier if the efficiency of the engine is 35%. And the calorific value of biomass is given as 16800 kilojoule per kg. And we are considering the efficiency of the gasifier is 0.75. So for more clarity, you can make this kind of block diagram. So this engine is used in gas training. So gasifier and gas training, this is a single system. So when we say efficiency of the gasifier, that includes gasifier plus training system, okay, which is 75%. So here power generation need to be done about 350 kilowatt, and engine efficiency is 35%, okay. And then what will be producer gas? So input to the engine is 1000 kg, because 3500 divided by 0.35, it will be 1000 kg. So that's the engine input, okay. So contribution of diesel and producer gas both are there in 1000 kilowatt, okay. So as we said, it's a 80% replacement. So 20% of this will come from the diesel and 80% will be from the gasifier, okay. So that way 80% is from the gasifier, and if we use it, okay, if we multiply it, it will become 1800 kilowatt, and then we can calculate the input of the gasifier 800 by 0.75, okay, because we know the efficiency of the gasifier, so this should be the value. And then finally we can calculate the feeding rate, because we know the calorific value. So mass of the fuel multiplied by calorific value, which will be equal to 1066.7 kilowatt. So from that we can calculate what will be the feeding rate, okay. So this is found to be 228.6 kg per hour. So in order to generate 350 kilowatt of energy, so we need to burn about 229 kg of biomass per hour, okay. So this problem will, or this exercise will give understanding how a gasifier system operates. Now move on to the biogas technology. So there may be anaerobic digestion or maybe aerobic digestion. So here we will be concentrating about anaerobic digestion. Okay, so aerobic means, in presence of air, this degradation of organic material takes place. But in case of anaerobic digestion, so in absence of air, this degradation of organic material takes place. So this kind of assembly is used for generation of biogas, okay, which can be used for generation of electricity as well as heat for cooking. Okay, so this anaerobic digestion composed of a inlet tank, fermentation chamber, and outlet tank. Okay, so here this we feed this biomass here, and then it goes to the fermentation chamber. It generates biogas. Okay, so about 33% of this total volume is occupied by the gas, and then gas can be supplied to the gas engine. And if we couple the generator, then you can generate electricity, and this gas can be used for cooking and other applications. And this slurry which is coming out from the digester can be used directly as a fertilizer in the paddy field, or we can enrich the quality of this slurry by doing vermicomposting. Okay, so we can generate valued product, and that gives a lot of entrepreneurship. Okay, because significant amount of fertilizer can be generated, and that too organic fertilizer, which is very, very healthy for the soil. Okay, so what we need to think, what kind of materials can be used as feedstock. Like we can use kettle dung, then vegetable waste, food and digestion means both vegetable waste and kettle dung, and then some kind of additives to increase the activity of the microorganisms, so that we can get the maximum gas production from the slurry. Okay, and then we need to see the microbial activity and microbial growth. then hydraulic retention time, then design of the reactor to maximize the gas production, right? Of course, we have challenges like purification of gas, because if we can purify it, then what we can see, we can get enriched quality of what is called biogas, which composed of about 99.9% methane, which is resemble like natural gas. So this already we are aware about the composition of biogas. It composed primarily methane and carbon monoxide and produced through the decomposition of organic matter by anaerobic bacteria in the absence of oxygen. And composition of gases depends on the feedstocks. And the impact of methane on the climate, that is already known to us. This methane is measured greenhouse gas, about 22 times dangerous than carbon dioxide. And methane contributes about 20% of greenhouse gases. And now see how this anaerobic process works. So here what happens, it involves a lot of microorganisms, and then there are different processes involved. And then we have to feed the what is called material, which composed of hydrocarbon, protein, lipids. Okay. So first what happens, this organic material converted to amino acid and sugars by using cellulitic lipolytic microorganisms, and this process is known as hydrolysis. And these amino acid and sugars converted to fatty acid by using fermentive microorganisms, and this process is known as fermentation acidogenesis. And then finally, this fatty acid is converted to acetate and hydrogen by using hydrogen producing microorganisms, and this process is known as fermentation and acetogenesis. And finally, this acetate and hydrogen is converted to methane by using microorganisms called methanogenic, and this process is called methanogenesis. Okay, so primary reaction takes place here because we are interested about methane formation. So how we need to maintain the health of the microorganisms, especially these microorganisms, is very, very important. So what are different reactions takes place? First, what happens? These feedstocks, this is glucose, we can say C6H12O6, which is react with water vapor, it produces hydrogen and acetic acid, and then carbon dioxide. Okay. Then again, this acetic acid converted to methane and carbon dioxide, and of course, in between, this ethanol is also generated, that is converted to methane and acetic acid. And finally, this carbon dioxide and hydrogen reacts with methane and H2O. So in nutshell, if we say the overall, what is the overall reactions taking place in a anaerobic digestion? This is something like C6H12O6 plus 3H3H4 plus 3 carbon dioxide. That means 1 mole of glucose gives 3 mole of methane plus 3 mole of carbon dioxide. This is the overall reactions taking place in a anaerobic digester. Let us see what is the efficiency of this conversion from glucose to methane. Okay, let us have a look in a practical sense. Like the molecular weight of and the heat of combustion of glucose is 180 and 16 megajoule. Okay, for glucose, and this molecular weight of what is called methane and heat of combustion is 16 and 55 megajoule per kg. So if we refer to these overall reactions, then 180 kg of glucose converted to 48 kg of methane, because it is 3 mole, 16 into 3 is 48 kg of methane. Then stored energy in 180 kg of glucose will be 180 multiplied by 16. Okay, because 16 is the combustion heat of combustion. Okay, so it will be 2880 megajoule, and stored energy in 48 kg of methane is about 2648 megajoule. So if we are interested about conversion efficiency, then what we can do, 2640 divided by 2880, it will give 92% conversion efficiency. So it's a very, very efficient process. But no, when we talk about the system level efficiency, it varies from say 40 to 60%. Okay, so there are some losses. But if you see this, it's a very high conversion efficiency. So this kind of technology is really very good technology as far as our waste utilization and energy conversion efficiencies are concerned. And there are some fuel properties. Okay, so if we consider with 40% carbon dioxide, it gives about 22 to 24 megajoule per cubic meter of calorific value. and without carbon dioxide it just goes up to about 36 megajoule per cubic meter. And also we can compare setting rating or octane rating with 40% carbon dioxide and without carbon dioxide. So it's about 110 and 130 respectively. And air to methane ratio for complete combustion is 10:1. Also we can see the biogas production and its composition. So if we compare fat, so it has the potential to generate about 1200 liter of biogas per kg of dry substrate. And in case of protein, it's 700, and then carbohydrate about 800 liters per kg of dry substrate. So fat, if we get fat, then it is more advantageous for us. And then methane percentage will be 67%, and protein, in case of protein, 70, and carbohydrate is 50, and carbon dioxide is 33, just 100 minus 36 is 66, 7 is 33, then 100 minus 70 is 30, 100 minus 50 is 50, okay? Also, we can compare this biogas with other fuels. So 1 cubic meter of biogas, normally, in biogas research, and then most of the time, we say in terms of cubic meter, means cubic meter of biogas per day, okay, in volume, we normally tells. So this 1 cubic meter of biogas equals to or equivalent to about 0.52 liter of diesel, 0.62 liter of kerosene oil, 3.5 kg of wood, 12.3 kg of cow dung cakes, 1.46 kg of charcoal, 0.43 kg of LPG, 1.6 kg of coal, and 0.47 kilowatt of electricity. Okay. Now, let us see the different factors which influences the performance of biogas plant. There is carbon nitrogen ratio, temperature, pH value, loading rate, hydraulic retention time, toxicity, and dilution and consistency of input, and effect of vegetation, biogas yield, and then effect of additives on biogas yield. So these are the methodologies we have adopted. Like first we adopted for design of biogas digesters, then scale study, then simulation study, then field study. So this kind of laboratory experiments we have performed. We take some kind of digesters. It's a fixed bed type or batch type digester of capacity 2 liter, and then gas is generated, and this is the thermocouple to measure the temperature inside the digester, and then gas formed here, and it goes through this pipe, and then it can be seen in the inverted measuring tap. So we can connect two, then see what happens. So that way we have done a lot of experiments with control and uncontrolled environment, and we have simulated, and finally we have installed a digester. So these are some of the experimental results of the our experiments. So this figure shows the gas production versus number of days. So what happens? It goes to maximum and then decreases. So similar pattern has been observed for all the cases. So cases means there are different total solid content of the digesters. Okay. So this digester C, what is here? Digester C is having very good cumulative gas production. It's about 11.09 liters, and its total solid content is 9.1 plus minus 0.5. Okay. And also we have compared our data with vegetable waste, because our plan is to mix these two in a field digester. So that's why we have performed the experiments in laboratories first, and that was implemented in the field. And this figure shows the variation of temperature and pH with respect to days. What you consider with time, it stabilized and becomes neutral. So what I was explaining about our configuration of this biogas plant. So we have used solar photovoltaic collector, and then solar PV for powering this pump, and this pump is used to circulate the fluid for this heat exchanger. So we have designed one heat exchanger which is installed in the digester. So it was a very complex design, and really it maintains very good temperature. So these are the photographs of the experiments what our students are doing. And here what is shown is the biogas production, variation of biogas productions with time. So it varies something like this, and temperature fluctuation you can see the ambient temperature variation. And here is the pH values. And what we did inside the digester, we have taken some points. First of while fabricating, we're in, and then we have defined some points, and then all those points we have inside the thermocouples, and these are connected to data acquisition system. So we know the temperature profile inside the digester. And then while doing this or installing this heat exchanger, you can see here what kind of variations we get. So this is very close by. Okay. So here you can see the difference in temperature. 20, then 25, then it goes to close to 30 sometimes. But here what happens? Temperature is constant. That means what? So by regulating this temperature, we can regulate the register temperature, and we can maximize the gas production, because if we can maintain this temperature, we can maintain the health of the microorganisms so that they can maximize the gas production. And also there are some rules of sizing this biogas plant. Like 1 kg of dry matter, how much gas can produce, and 1 kg of fresh kettle down, how much dry biodegradable mass can produce. And 1 kg of fresh kettle down has volume of about 0.9 liters. And 1 kg of fresh kettle down requires an equivalent volume of water for preparing slurry. So this information is required for sizing a biogas plant. So let us take this an example. So we have generator, and then we need to generate power of 2 kilowatt, and we have engine and then biogas plant. So example is something like an engine generator system running on biogas is proposed to be installed in Assam Engineering College to produce 2 kilowatt of electric power. Estimate the volume of the digester of the biogas plant required. So calorific value of the biogas is given, efficiency of the generator is 90%, and efficiency of the engine is 30%. Okay. So by considering that, we need to find out how big biogas plant is required in order to generate 2 kilowatt of electrical power. Okay. So we can use our some thumb rule, like power input to the engine, that is already known to us, 2 by 0.9, because generator efficiency is 0.9. So power input to the generator is 2.22 kilowatt. Yeah. Yeah. So this is power input to the engine. So here, because we need to find out the efficiency of the engine. Okay. So already we have given this efficiency has been given, that is 0.3. So here power requirement will be 2 by 0.9 into 0.3. So it will be 7.5 kilowatt. For at this point it is 2.22 kilowatt. And then quantity of biomass required is 7.4 divided by 20,000, which is calorific value is given as 20,000. So it will be something like this. And then for continuous operation, biogas required is 36,3600, and then 24. So it becomes 31.96 cubic meter per day. Then dry cow dung required is 31.96 kg per day. Then mass of fresh cow dung required is already we can apply our thumb rule. So this should be something like this. And volume of the slurry you can calculate. And if we consider hydraulic retention time, that means the 40 days this slurry will be inside the biogas digester. Okay. So if we consider this, then we can calculate the slurry volume, and then digester volume will be about 28768 liters. So it will be about 29 cubic meter. That means 29 cubic meter biogas plant is required to produce 2 kilowatt of electrical energy. Okay. So feeding can also be calculated, how much feed is required, right? Now let us have some biodiesel, because we have included some component of biodiesel, because completely we are trying to localize the system, power generation system. So biodiesel was collected, and it was processed, and its properties were investigated. So finally, we have done the experiments in IC engine, and we have got some data and how this brake thermal efficiency is varying. And FD means fossil diesel, and then Jethrofa blend, and then Jethrofa 15%, 20%, all the different blends. We have done the experiments, and also we have generated this cylinder pressure versus crank angle. And also you can see in emission characteristics, this figure shows the variation of carbon monoxide, hydrocarbon, and NOx formation with respect to load. If load is increases, means what happens? The NOx formation increases. That's a disadvantage of this kind of system. And with increase in load, this carbon monoxide is decreasing. Okay, and for lead is hydrocarbon. So with increase in load, no, this hydrocarbon is also decreasing. Okay, and here is the result of the experiments with biogas and producer gas. Okay, so here is a break thermal efficiency with load, and then we have this FD means is fossil diesel. Only diesel is used. Diesel plus biogas and diesel plus producer gas. You can see the variation here. Okay, so different combinations we have tried. Also, we have developed this Venturi, and then Venturi gas mixture is a conversion diverging section of the throat, and it's a very complex unit, and we need to optimize the angle of incidence, and the nozzle angle, and the ratio between the diameter and the diameter of inlet and outlet manifold. So we have challenged we have faced a lot of difficulties because it was a great challenge to make this what is called mixing device. Okay, so we have devised this system. It looks something like this. It's a converging nozzle, that's then diverging nozzle, and this is like a solid. No, we have not remove the material here. So remove, if you see from the front, it's like a solid block, but it's not. It's a hollow, which tapered. So it is something like this, and then this is the throat section. So sealants is here, throat is there, and then we have to maintain many holes. Okay, one for producer gas, one for biogas, and one for air. Okay, so all the things has to be taken care, and finally we did it. And these are the result of the experiments. We have done some numerical experiment before we have fabricated the system. So you can see this pressure variation. This 0 means that's a neck, and it reduces and it goes up, which increase in x direction. And then velocity is maximum at the throat, and then it decreases. And this turbulent kinetic energy versus s direction, you can see at 0, it was something like very less. And when it goes down or downstream, so turbulence is increases. So this turbulence increase is advantageous because more turbulence means more mixing. So that's what we want. So all the gases, if it mixes well, then there is no problem of combustion. So and also we can these are results of the numerical experiments. What you can see initially, this is something like this. When it mixes slowly, so it mixes, and then finally what we get, that's a proper mixing. Okay. So that different combinations we have tried, and we have used in our experimental investigation. So this is the system. So okay, so different position you can see here. So this is something like this, and it's a hollow thing. It's a tapered. Okay, so you can see how it moves. It goes something like this, and then mixes, and it goes out. Okay, so that's how it works. So this color indicates different gases. So we have producer gas and biogas. Again, in the producer gas, we have carbon monoxide, hydrogen, methane, and biogas we have carbon dioxide, then methane. So all the gases, and then air will be coming from this side. Okay, so that's how it is modeled. And also we have done some kind of modeling and optimization of diesel biogas dual fuel decentralized power generating unit using response surface methodology. So what we can do, we can optimize, because see how many times we will perform the experiments. So there are some limits. So we need some kind of guidance which can guide us the optimum number of experiments to be performed to get the best results. So in order doing that, what we are doing, we are utilizing response surface methodology. It's a software. Okay, so here what we did, we have varied load, then compression ratio, then injection timing, and then the output, what we're expecting, combustion behavior, combustion should be proper, and then emission should be as per our required norms, and then thermodynamic efficiency has to be as per our requirement, right? So these were the variables what we have considered. Okay, compression ratio was varies from 17 to 18 at a step of 0.5 increase, and then injection timing was 23, then 26, 29, 32. These are the parameters we have considered. And output parameters where, as I said, these are combustion parameters, then performance parameters, and then emission parameters. So it runs for 80 experiments, and here this analysis of variance ANOVA is used for developing the primary model, and closeness of R squared towards 1 signifies the best fitting of the data in the model, and the input parameters are correlated with output response using quadratic model. Okay, that is suggested by this response surface modeling. Okay, so these are the mean of those variables, and standard deviations and adjusted R squared and R squared. These are given by the model, and they have suggested a quadratic model. So that's why they have given BTE, how this BTE will vary. Okay, once we know injection time in CR and then load, then we can calculate what is the BTE, then peak cylinder pressure, then NOx. This can be calculated by using the input variable that is suggested by the model. Then we'll move to the optimization. Okay, so this optimization is something like we have considered now these ranges of the load. 20 to 100% load will be there. Then compression ratio 16 to 18. Okay, so we got some idea in that range. It will operate. And injection timing 20 to 23 to 32. Then brake thermal efficiency about 4 to 25. Then peak cylinder pressure is given. And then we have to specify which parameter to be maximized and which parameters will be minimized. Like NOx has to be minimized, and of course brake thermal efficiency need to be maximized, and peak cylinder pressure need to be maximized. Okay, and then CO, HC, and NOx need to be minimized. So while doing so, this now optimized condition, what this model gives is about load. If we maintain a load of 65.45%, compression ratio of 18, injection timing 32, then brake thermal efficiency 16.54, and then peak cylinder pressure 51.26, biomass to fuel ratio is 1.93, NOx 16.68, hydrocarbon 98.42, CO 130.02, and then desirability, this parameter should be close to 1. It is 0.96, means very, very close to 1. And since we are using an engine of capacity 3.5 kilowatt, so 3.5 kilowatt of 65.45 will give 2.28 kilowatt. Okay, so at these conditions, you are expected to get the best efficiency of the engine. And also we have done some kind of economic and financial evaluation of the technology package, and see payback period, how we have calculated, and net profit value. And then when we are considering economic evaluation, we have considered all those parameters. Levelized unit cost of electricity, net cash flow, payback period, the net present value, and then annual cost, the annual maintenance cost, the annual fuel cost. Okay, so these are the formulations, and then finally what we get, LUC value is about 30.38, which is somewhat higher, but of course government support is also required. And payback period is about 7.9, about 8 years. And if this LUC value after payback period is over, it will be about 17.39 rupees. And here we have tried with different fuels like biomass power plant and then producer gas power plant. So if you combine it, then what we'll get. Okay, and what will happen after payback period is over, and if we do not use local distribution. Okay, if we do not use local distribution, then what will be the per unit cost? If we use local distribution, what will be the per unit cost? So these comparisons are made. Also, this is quite interesting because what we have calculated, the amount of feed material required depending upon the different situations. Okay, suppose sometimes what happens, we have some kind of raw material for thermochemical conversion, but we have very less amount of raw material for biochemical conversion, which is required for biogas technology. So that way, this chart will guide you which composition to be used. Okay, so for gaseous fuel, if we consider the 70% of energy will come from gaseous fuel, So this gaseous fuel may be producer gas or maybe biogas. And diesel, from diesel it will come 30%. And second case is 80% gaseous fuel. And this energy may come from producer gas or maybe biogas. And diesel will be 20%. And third case is 90% energy will come from gaseous fuel. This gaseous fuel may be producer gas or maybe biogas. And then 10% will come from diesel. Okay. So different combinations have been tried, and it is found that this raw material requirement is very, very high at this condition when we are using 90% gaseous fuel. So under this condition, producer gas and biogas, so that's 100%, raw material required is about 1200 kg per day. And then here what happens? In this case, raw material requirement will be lower. So if we maintain this category, so 80% biogas and then 20% producer gas. Okay, so that's how it is minimum. Okay, minimum raw material requirement will be in this case, and maximum raw material requirement will be in this case. Okay, so this is a very important chart which guide the people to take which technology to be used based on the availability of the raw material. Now let us see the downstream process. What happens once we have generated the energy from the gaseous fuel, what we will get the exhaust gas. Okay, so exhaust gas is at very high temperature, and that can be used at different temperatures. Okay, so we can have 3 heat exchangers, and this heat exchanger is meant for the 3 different applications. One is for slurry drying, and second one is for refrigeration. That's a vapor absorption refrigeration, and third one is for making what is called distillate. Okay, so that's what is shown. So I will not go in deeper because already I have consumed a lot of time. I think I should conclude now. So from this work we have published many papers, and then still there are some paper under review. So hopefully it will be published soon. And this is the before I conclude, let us acknowledge SARB of Government of India. This work is a part of that project development of remote renewable energy technology package for clean power generation in remote utility. And just now, 2-3 months back, we have completed this project successfully. Now we need to identify some village to install this complete package for generation of energy and then other downstream utilities. So in summary, we have developed the gas mixing device successfully, which is very, very important for us, and demonstrated the capability of utilizing gaseous fuel and liquid fuel together, because we have used biodiesel as well for generation of energy, and successfully developed an efficient anaerobic digestion plant and developed an integrated experimental facility for clean power generation. So this is our group. So Demangsu was assistant project engineer in the project. So his work is to make all these financial matters and then procurement. But at the same time, he did a master degree from the project. And Somor is doing PhD. So his work is on biodiesel blends, emulsification, then biogas producer gas mixing devices, then design and development of gaseous fuel and air mixing devices, and financial evaluation. And Sairam Bosumatari, he's a faculty of CIT Kokrajhar. So he's also doing PhD under the QIP, and his work basically on this biogas part, and then he's doing some kind of devices for storage of biogas. And Akash Kamble, he has completed master degree, and he was working on that vacuum operated distillation system. And he's Harishan Muigai, and he's from Kenya. He's one of my foreign students. So he's basically working on this pyrolysis part of his experiment. So he's submitting his PhD soon in the coming December. So thank you very much for your attention. So I think I have taken your significant amount of your time. Okay. So thank you very much.
Thank you, sir.
Okay, thank you, Mr. Dr. Kalita. It was very nice, informative session that you have delivered. So I am quite definite, participants will be benefited from your lecture. Now there are some queries, Mr. Kalita, if you can permit me, I can read out.
Yeah, maybe I can also see here somewhere.
Okay, have you got it? Should I read it out, sir?
Just a minute. Check.
Okay, the first question is coming. I one by one I'm taking.
Why I could not see their comments.
Okay. Okay.
Let me see. I could not see their comments. So why this is so? I should see their comments.
Should I take it one by one?
Yeah.
Yeah. The one question is being asked by Mr. Ratnadeep Malakar. He is asking, what is the material used to build the biogas digester and what measures are taken to maintain the temperature during the winter season?
Its material is FRP, and our what is called what is that material? Our construction material is like bricks and all that we have used in the, as a material. And then winter, that's why in summer we don't need that kind of arrangement. Only some kind of, maybe in a day 2-3 hours is fine to operate this our PV and then solar flat plate collector to maintain the temperature. But in winter we need to operate this system to maintain the registered temperature.
Okay, the next question is from Apalak Sharma. He is asking, sir, in biomass conversion, how the combustion is initiated?
Oh, already glucose already I have said there. I think if he has attended sincerely,
he is
that
a
can
student.
be configured. No, I have given the problem also.
Mm-hmm.
Like glucose is there, glucose is converted to carbon dioxide and hydrogen. And 1 mole of carbon dioxide, 1 mole of glucose is converted to 3 mole of methane, and from that we can figure it out. It is very easy to see.
Okay, so in another question query by Shritiras Talukdar, it's being asked, how is the anaerobic digester's chamber, the temperature, as you said, mentioned, that 35 degrees centigrade, how it is achieved?
Yeah, by designing the appropriate heat exchanger.
Yeah. Actually, these are students, Mr. Kalita.
Yeah.
So they are studying, they are also reading this subject. So they are asking from that point of view. Another question by Tritiras Lakar, he is asking, is there any significant difference of using different types of beds in the biomass gasifier?
What is the question?
Different types of beds.
Which?
Bed, B-E-D, bed. Different types of beds in the biomass gasifier.
Biomass gasifier beds, you can say BED beds, right?
BED, beds.
No, beds no. See, there are fixed bed, then fluidized bed. Okay. Fluidized bed means moving beds. Fixed bed means bed is fixed. Okay. So here what happens? Fluid and this raw material moves from in the column. Actually, that move. If you consider, if you cut a section, that section composed of solid and gases. So when we applies more air from the bottom, that what is called bed will move from the bottom to the top. So that's a bed. So what happens if you are working on fluidized bed? Then that's a high capacity. So large scale for power generation, we should go for moving bed system, and for a capacity up to say 500 kilowatt. So we'll go for fixed bed capacity or fixed bed biogas plant. Producer, what is called gasifier plant.
Okay. Now then, Ratnadeep Malakar, he has again asked, can we use crop residues as feedstock for the biogas digester? What will be the possible challenges in that case? Crop residues.
Yeah, see, first, as I said, we have to do some kind of pre-treatment. So pre-treatment is very, very important for this kind of feeding. Okay, but straight away if we feed it, then it will be difficult, because as I said, the scum formation is a quite challenging problem. Okay, so if this crop residue is introduced without treating, then it will cause different problems like scum formation and other issues.
Okay. Then lastly, here's asked again, what are the prominent techniques to increase the amount of methane production from more than 60 to 70%?
Ek minute, Rashi, just a question and answer session. Can we use crop? Okay. Lastly, what are the prominent techniques to increase the amount of methane production?
Yeah.
Increase the methane production. So
More
first thing,
than 60 to 7. Yeah.
Substrate, and then techniques means what you can do. There is no techniques to increase the methane production. So first thing, we can maximize the biogas production, but substrate plays a key role. But after generation, we need to clean it. Then we can increase the methane production.
Okay. Okay. Thank you. Then how the Kamal Talukdar has asked how retention time for particular unknown biomass is calculated and whether it can be changed.
See, this hydraulic retention time is a design parameter, Kamal. So you have to design a digester. It is mathematically represented by volume of the digester divided by volume of the feed material feeding daily. So that will come in days. Okay. So this is a location specific problem. So if we are designing a biogas plant for a state like Ladakh, then this hydraulic retention time will be very, very long, because it takes longer period of time for digestion. So while designing, we need to pay attention about this hydraulic retention time. So if we design same biogas plant for a state like Gujarat, then hydraulic retention time will be less than 40 days. Okay, for Ladakh it will be 120 days. Okay, so this is something like that.
Okay, he has again asked, is anaerobic digester advantageous than aerobic digester?
Of course. Of course.
After extracting biogas from digester, whether cleaning of the inlet tank, outlet tank, and digester are needed?
After extracting biogas from the digester,
whether cleaning
of inlet tank already clean, there is no relationship of biogas taking and cleaning. This question is not valid. Question is not valid.
Okay.
Yeah.
Okay, now there is some raised hand actually. Kalita, just wait. There is some raised hand actually. Okay, and someone has raised. Okay, Mr. Venkatas.
Yes, sir.
Hello, Doctor. You want to ask something? Okay. Good evening. Good evening. Okay. You want to ask something, Mr. Kalita? Yeah.
Sir. Hello.
Please put your question.
Sir, this biogas, no, sir? What are the policies needed, and what are the technology needed for this bottling, sir? Actually, bottling kind of things.
Please say again. Bottling. You said bottling of biogas plant.
What are the new technologies required and policies from government side to start a bottling plant, biogas bottling plant? Nowadays, that scheme bio-CNG is in news, no, sir?
So, yeah, that's bottling. I don't have much idea, but what I know is GAIL, Gas Authority of India Limited, they have called proposals for storage facilities, because what they are planning. See, natural gas is coming through in a pipeline. And then if you are generating some biogas, or say you have a biogas plant, so in order to provide the generated biogas in that pipeline, we need to clean it. So that way, there is a proposal from GAIL. So you can actually gain money out of generating and then providing the energy to the pipeline. But as far as policies for making bottling, I'm not sure about that, because I'm not dealing with that actually.
Thank you, Kalita. Sir, just last one more question. So this biogas production, no, sir? So people are thinking generally they are using elephant grass. So which will be beneficial, whether it is directly cattle dung or the elephant grass? Because Government of India has one more dream job.
Please speak near to your mic, because your voice is very low.
Sir, this Government of India, they are thinking about doubling the farmers' income by 2022. So is it viable if the farmers has been given to chance to grow the elephant grass to produce bio-CNG?
Elephant grass for producing?
Bio-CNG, biogas basically, and then bottling it. Bottling is secondary, at least for biogas.
See, things are different. So if you are telling about elephant grass, see, that has to be rooted through thermochemical conversion, not the biochemical conversion. So for that we need biomass gasifier. So we should be very clear about the kind of technology to be used for a particular kind of feed material. So here in the anaerobic digester, we are not concerned about organic matter, but in case of thermochemical conversion or biomass gasifiers, we have to go for that kind of products like plant and all. So yeah, I think government is doing some kind of initiative, because I had a talk with DST people and they are making some kind of I think strategy to make some kind of hydrogen by using this thermochemical conversion process. So I think government is doing it.
Okay, sir. Thank you, sir.
Any other questions?
I think there's no questions. Okay, sir. There's no more questions anymore. Thank you, sir.
Yeah.
Thank you for your valuable words. That was quite helpful. And I think our participants have also got some new ideas. So thank you very much. Now I'd like to go for the second session. I'd like to go introduce you all the second lecturer of the today's session, Dr. Monoj Bardalai, sir. Dr. Bardalai has graduated from ASSAM Engineering College, completed his master's and PhD in renewable energy conversion from Guwahati University in 2017. Starting his teaching career at TEQIP University, Tripura, Dr. Bardalai is currently serving as assistant professor in Tezpur University. His research areas include renewable energy, heat transfer, and thermal engineering. Having 12 years of teaching experience, Dr. Bardalai has published 7 research papers in reputed journals and many national and international conference papers. Recently, in 2019, he was awarded with Outstanding Reviewer Award by Journal of Air and Waste Management Association from Taylor and Francis publication. So we are glad to have you among us, sir. Now I request Dr. Bardalai, sir, to share his few words for us. The platform is yours now, sir. You can share.
Hello, Manoj.
Yes,
Yeah,
I think I am audible.
Yeah.
Yes,
fine.
Yes, okay.
Fine.
Okay, thank you, Vidisha, and very good afternoon to all, and all the team members of this ETBP 2020. And particular thanks to Prasanto Chaudhary sir for inviting me to deliver a talk in this webinar series. Today, the title of my talk is, just a minute. Okay, let me share the screen. Is my screen is visible?
Yes,
No,
sir.
Manoj,
Yes,
has it come? Vidisha, has it come?
Yes, sir. Yes, sir.
Okay. So the title of my today's talk is role of characterization in the research of bio-waste conversion. As we know, most of the time the biomasses are considered as a waste product only, and therefore it needs the disposal. And because of this disposal, sometimes it creates some problems, in fact. So it is always better if these biomasses can be converted to some other kinds of products. Even many researchers are doing in this kind of work, developing different types of conversion techniques and also the methods. As we can see that our previous speakers already have explained lots of the technologies, new technologies and emerging technologies, how to convert the various types of biomasses into different useful products. Now, thing is that how can we say that this kind of products are really useful for our different kinds of purposes? So obviously, for that we need to evaluate the properties very properly, which is basically known as the characterization. Generally, some thermochemical, then physical, and morphological, thermal, these kind of properties are evaluated. And nowadays, we can see that lots of new technologies and methods and techniques. These are coming up, and using this we can precisely evaluate or analyze lots of properties, and we can do the various characterization. And it is also found, and I believe that this kind of characterization definitely helps to identify the various types of products and its nature, how it can actually helps or to utilize the different types of our purposes. So this is how the characterization has a very big role in in this kind of research of bio-waste conversion. So this topic basically is meant for the beginners who are doing some this kind of bio-waste conversion in this type of work. So I think for them it will be helpful for this. So let us go for my contents of this topic. So these are the main contents of this talk. First of all, the types of various bio-waste conversion, then the different types of products that can be obtained from the bio-waste conversion, then the characterization of the samples. So out of this characterization, we can see basically the proximate and ultimate analysis, which is very common to all kinds of solid samples. Then TZ, DTA, and DSC. So these are basically the thermal characterization or thermal analysis based on which lots of analysis can be done. Then the XRD, this is basically the X-ray diffraction. So with the help of this, we can do the analysis of crystallinity and amorphous kind of nature of the sample. Then for chemical analysis, we can use the FTIR. This is Fourier transform infrared analysis. Then for morphological type of characterization, we can use the ASSAM and BET. So we'll explain in details about this. Then for chemical characterization, we can use the GC MS kind of coupled devices. Then very common physical properties for the liquid products obtained from the biomasses, such as viscosity, density, water content, and then flash point, fire point, pH. So all these kind of properties must be measured or must be calculated because these are very common properties that must be known before doing any kind of characterization or before going to use the product to any kind of purposes. And finally, we'll see about something like biodegradability analysis of some liquid product obtained from the biomasses. Conversion of bio-waste, most of the time, if we see that the main products of biomass conversion, whenever the biomass is converted to some other products, then basically we get the solid, liquid, and gaseous kind of products. And if we see the type of conversion, lots of type of conversions can be seen. So out of that, in a very simple way, we can see that the direct combustion or direct conversion process. So in this process, if we have to define that it is very simply, if we ignite or if we burn a dry biomass, definitely it will give some heat. So this is how it is converted directly to some other kind of form. But in this kind of process, the products or the energy, whatever is obtained, so this is not actually measured, or there is no scope to measure it. In fact, apart from this heat energy, it also produces some other kinds of products, so which are not actually evaluated. So this is how it is somewhat not so much useful and not so much convenience. So then another process is that it is a physical conversion process. In physical conversion process, normally the biomasses are made into some pellet form, and then it is placed in some machines where these are crushed, and some other kind of products, such as liquid kind of products, can be obtained. Of course, directly this kind of product cannot be used. It has to be refined using some refinement process. Then another very common method, although we are not using this, this is biochemical method. So in this method, we take the help of some enzymes or maybe yeast or maybe some microorganisms. And in this kind of process, generally the products are in the liquid form, such as methanol, ethanol, biodiesel, etc. Finally, the thermochemical method. This is the most common and convenient method where we basically apply some heat, and because of this heating, some lots of actually thermochemical reaction take place. And we see that under these thermochemical methods, basically two types of process are very common. That is the pyrolysis and gasification. In both the cases, we need to apply the heat and we need some experimental setup. Although in the pyrolysis case, it is somewhat, I mean, simpler as compared to the gasification, and it also consumes somewhat lesser space. But again, some more differences are there in between this gasification and pyrolysis process. That pyrolysis process, the temperature range is somewhat lower than the gasification. And in pyrolysis, normally we do not use the oxygen or maybe very negligible amount of oxygen. Whereas in the gasification, after certain stages, oxygen is applied. So this is how this type of various processes are there under the thermochemical conversion. So since I did some work on thermochemical conversion processes, and here I actually going to show some characterization of the products of obtained from this pyrolysis process, which is under thermochemical conversion method. So for that, I took some samples. This kind of 4 samples. The first one is the bale cell dust. Second one is the areca tree dust, and this is the teak tree sawdust, and this is the rice husk sawdust. So these are seen as in the powder form, because in the laboratory scale, whenever we do the pyrolysis, this reactor basically is very smaller in size, and also the size of the feedstock must be very smaller, less than always maybe one millimeter, or maybe less than 0.5 millimeter. So therefore, we first have to grind the feedstock so that it comes under the range of feedstock size up to 0.5 or lower than 0.5 mm. And one more important thing is that while we prepare this kind of feedstock, its moisture content must be maintained below 10% or maybe around 10%, because if the moisture content is somewhat higher than 10%, it creates some problem in the conversion process. So this kind of preparation can be done very easily using the very conventional mixer grinder maybe, and then we can use some standard size sieves so that we can get the required particle size of the biomass feedstock. So this is another type of feedstock. It's basically a combination of both biomass and coal, and we can look at here that this size of this feedstock is quite higher than this type of feedstock, because this kind of actually feedstock I used for another purpose, which I will not concentrate much in this part, because this kind of sample was used for the gasification purpose only. So anyway, this is how we can prepare the various types of feedstock before doing the experiment or before doing the various types of analysis. Now, if we look at the composition of the biomass, as we all know that the biomass is consists of mainly 3 components, such as cellulose, hemicellulose, and lignin contents. And generally, their range lies within this given value, such as cellulose will be within 50%, and hemicellulose will be within 25%, and similarly the lignin will be 25%. Based on their nature, they are quite different to each other. Say cellulose is basically responsible for producing the vapor if we use it for if we use the biomass for the thermochemical conversion such as pyrolysis. Similarly, hemicellulose also responsible for producing the vapor, but the lignin is quite different than cellulose and hemicellulose. So this is a very complex structure actually, and it is a three-dimensional polymer, and this is basically responsible for production of the solid products such as the biosar. And we did one experiment, or we did one evaluation to get the cellulose, hemicellulose, and lignin content for the bale cell dust. And this was obtained as 40% for the cellulose, 28% for the lignin, and 30% for the lignin. And this is a very actually very lengthy process to evaluate this kind of cellulose, hemicellulose, and lignin. So for this, we can use this kind of equation. The cellulose can be used, can be obtained by using this relation, that is ADF minus ADL, where ADF is the acid detergent fiber and ADL is the acid detergent lignin. Similarly, for hemicellulose, this is obtained by NDF, this is neutral detergent fiber minus the acid detergent fiber. So again, all these acid detergent fiber, acid detergent lignin, neutral detergent fiber, all these things again can be measured using some solution like acid detergent solution and neutral detergent solution, something like this, and then we can use the weighing method after doing the ignition and so on and so forth. But whenever we do this, we must to follow some standard methods such as the ASTM standard. So in this case, we used the ASTM standard such as ASTM D110596 protocols. So these are the schematic diagram for thermochemical conversion. In the first diagram, we can see this is a very simple and lab scale pyrolysis setup. Here we can see the main components are basically the first, this is the reactor under which we apply the, or we put the biomass samples. Then it is heated using some heating heater, that circular or cylindrical heater, which will surround the that reactor. Then when it is heated, due to pyrolysis, some vapors will be produced, and these vapors basically is allowed to pass through a pipe through a condenser, so that this condensable gases condense down, and it produces some liquid, which is known as the pyrolytic liquid. And this kind of pyrolysis process generally run for 1 to 1.5 hours. And after this completion of this pyrolysis process, we can collect the solid product as well from the bottom of this reactor. And to enhance the flow of the vapor through this pipe, another one nitrogen cylinder is used, and a flow of nitrogen is always applied here continuously or maybe intermittently, so that the vapor produced within this chamber can go outside. And if we observe, then in the pyrolysis process, generally the products of the pyrolysis are influenced by many factors, such as the pyrolysis temperature, at what temperature we are doing the pyrolysis. For example, whether we are doing at the 450 degrees Celsius or maybe or higher temperature. Similarly, the condensing temperature, at what temperature we are condensing the this vapor, then rate of heating, then the flow of nitrogen, then obviously the type of biomasses, because all these things depends on the raw properties of the biomasses. Then the size of the feedstock, as I have already shown in the previous slide, that there is a big role of on the size of the particles. So based on this factor also, it influences the properties of the products. Similarly, some of the researchers are doing also application of catalyst with the biomass sample. So with the application of this catalyst, most of the time it is found that the products obtained from this pyrolysis process are improved. And here we can see this is schematic diagram for gasification process really, but will not be concentrated here much. But here also lots of components are there, but the main component is the reactor here. So here you can see the photographs of the reactor used for the pyrolysis process. This is the reactor used for the pyrolysis process, and this is the photographs for the gasification setup that is available in the Tezpur University, and this is the reactor used in the gasification process. Now, since as I told that I will be more concentrated on the properties obtained from the pyrolysis process, which is under thermochemical conversion. Although there are two types of processes under thermochemical conversion, that is pyrolysis and gasification. So if we see the products obtained from the pyrolysis are basically the gas and solid. But when these gases are condensed, then it produces some liquid products. But some uncondensable gases are also there, which is not able to condense, so it goes to the environment, or someone may collect also. So this is how, if we condense down, some liquid product is found, that is the pyrolytic liquid, and within this liquid, if we analyze, this kind of compounds are found, such as alcohol, aldehyde, acid, ketone, etc., etc. And solid compounds. This is basically the biosar that is obtained after completion of the pyrolysis. So these are composed by very high molecular weight compounds. And finally, if we see about the gaseous products, which is known as also syngas, and in this gaseous products, we can see the various products such as carbon dioxide, carbon monoxide, methane, etc., etc. Here you can see this is the solid product obtained from the pyrolysis, which is also known as biosar. And this is the liquid product obtained from the pyrolysis process. We can also see the product distribution of the pyrolysis process with the temperature. If we increase the temperature, say for example 450 to up to 600 and more, something more than that, then we can see that the yield of gas continuously increases, whereas the yield of SAR continuously decreases. So why it is happening? Because as the temperature increases, we know that in the pyrolysis lots of chemical reactions take place, and because of this some secondary cracking, and because of which more cracking is observed, and because of which the gaseous products or gaseous yield increases. At the same time, if we look at the solid products, that is the biosar, so because of the secondary cracking with the increase of temperature, its yield decreases because of the secondary cracking of the SAR particles. So this is how it decreases. But interestingly, if we see the liquid products, that is shown by the red line, that at the beginning its yield increases because of the decomposition of cellulose and hemicellulose. As we have seen that generally the production of vapor, and from vapor we can get the liquid product. So this vapor production generally obtained because of the decomposition of cellulose and hemicellulose. So this happens up to maybe 500 or 550 degrees Celsius, And after that, there is not much, no more cellulose or hemicellulose is found. So its yield does not increase after this temperature. So it will remain constant and all. So this is how we can see the product distribution of the products of pyrolysis process. Now the characterization. As we have, I have already explained that characterization plays a very important role because without doing the characterization or without evaluating or analyzing the products, we actually cannot proceed for further application of these products. And after doing the proper characterization only, we can say that what kind of biomass will be applicable for what kind of purposes, and also what kind of products will be used for what kind of purposes. For example, sometimes the products obtained from the pyrolysis may not be useful as a fuel purpose, but it may be useful for other kind of purpose. For example, for the agricultural purpose maybe. So this is how we can see the various applications by doing the proper characterization of the properties. So first of all, this proximate analysis. So this is very common and very basic characterization that is done for all the solid samples, maybe the raw biomass and maybe the solid products, that is the biosand. So in the proximate analysis, we generally evaluate the volatile matter, fixed carbon, and ash content. So to measure the volatile matter, first of all, we have to heat the sample up to about 900 degrees Celsius without the presence of oxygen. Then all the volatile matters will volatilized. Then we can, this is how we can segregate and we can estimate the volatile matter present on the sample. And very good information can be obtained from the volatile matter present in a sample, that if the volatile matter is higher, then we can say that that kind of biomass is basically will be suitable for conversion to the liquid products such as bio oil or pyrolytic oil, because volatile matters are basically responsible for cellulose and hemicellulose. Similarly, for the fixed carbon, we have to heat it up to 950 degrees Celsius with a limited amount of oxygen, because the fixed carbon are not volatilized, but it can be oxidized. And it basically comes from the lignin kind of element of the biomass. And finally, for ash content, we have to complete burn the sample, and then whatever residue is found, that is the ash content. So this is how various types of this volatile matter, fixed carbon, and ash content elements are can be estimated. For all these volatile matter, fixed carbon, and ash contents have a particular role in the or influence on the products. Say for example, if the ash content of the raw biomass is very low, then we can say that it may be very much suitable for the bioil production, because higher ash content generally reduces the calorific value of the sample of the products that is obtained from that sample. And also in the ash content, some minerals may be present which may be not suitable for the fuel purpose. The proximate analysis basically of two types. One is ash receipt basis and one is the dry ash free basis. So ash receipt basis means whenever we do this kind of calculation as the sample, whenever it is received as usual. And dry ash free basis is a theoretical kind of process where we generally eliminate the moisture and ash content. So in that case, we only consider that the sample is composed by volatile matter and fixed carbon only. So to perform this kind of proximate analysis, again, we have to follow some standards, ASTM standards, that is American Standard for Testing Machine. So in that case, we used this ASTM standard such as ASTM D27148. So another ASTM standards are available out of that this is another ASTM D317289. So someone may use this kind of standard as well. So these are some results of results obtained from proximate analysis from different biomass and each solid products. For example, if we look the volatile matter, suppose, and also we can see the moisture content. Obviously, in the biomass, the moisture content will be higher. As I said, it should be actually around 10%, but it may be somewhat higher. Sometimes say it is found 11 or maybe around 12%. But in the biosar, it will be very less because all the moisture content is evaporated during the pyrolysis process. And similarly, we can see this kind of trend for other samples as well. Now, if we see the volatile matter, suppose in the bell cell, the sample, the volatile matter is very high, around 91%. But if we see the biosar, this is very less as compared to the biomass. So this indicates that it may be suitable for bioil production because the volatile matter basically responsible for liquid yield production once it is condensed. Similarly, for other biomasses also, we can see that this kind of volatile matter is quite higher as compared to the biosar. But if we see the fixed carbon are always higher in case of biosar. And one important thing we can conclude from this kind of result that if these biosars are applied for agricultural purpose, then it will be very useful because this higher fixed carbon materials are very much useful for the soil amendment. Similarly, if we go for the ash content in the biosar as relative to the biomass is quite higher. Say for example, rice has biosar, it is 29.06%, and for areca tree dust biosar is 24.1%. So this kind of biosar having higher ash content can be used again for the agricultural purpose, which actually gives some additional fertilizer effect. So this is how we can have some basic idea about the products based on their properties. Then ultimate or elemental analysis. So this is also very basic analysis that is done for both liquid and solid products. This is called the qualitative and quantitative in the sense that in this kind of analysis, we find out the type of elements present on the sample as well as its percentage. So in this purpose, we can use a digital CH analyzer. This CH analyzer is basically used to estimate the percentage of carbon, hydrogen, nitrogen. But oxygen cannot be directly obtained from this kind of analyzer because oxygen is also a very important element in the biomass sample or the products of biomass samples. So once we know the carbon, hydrogen, and nitrogen, so oxygen can be estimated by using the difference method from the 100 or 100%. And if we talk about the sulfur content, because sulfur content is very much negligible in case of biomass sample, although it is significant in the fossil fuel such as coal, etc. So the CH analyzer is sufficient for doing this kind of elemental analysis. Now, after doing this elemental analysis, that means obtaining the carbon, hydrogen, nitrogen, oxygen amount, one can develop the empirical formula of the sample. So we'll show how to find out this and how this looks like. Also, after getting the carbon, hydrogen, and nitrogen and oxygen amount, one can find out the calorific value as well using this Dulong formula. This is very popular formula. That is the Dulong formula, and this formula can be given here as like this. Also, calorific value can be estimated using a bomb calorimeter. Nowadays, several types of precise or very accurate automatic digital bomb calorimeters are available, so one can use this kind of bomb calorimeter as well. So after doing this, or after calculating this kind of calorific value both by theoretical process like Dulong formula and using the calorific using the bomb calorimeter, one can compare both the values, and there should not be much difference between these two values. So this is how some analysis can be done. So here you can see from the results of the ultimate analysis from different biomasses and their products. Particularly if we see the carbon content, suppose for the biomass like bell cell. So here in the biomass, the carbon content is relatively smaller or lower. Then in the liquid product, that is the bio oil, or we can say pyrolytic oil as well. So for the bio oil, it is somewhat higher. And again, the solid product, it is biosar, it is the highest value. So this is how it gradually increases from the biomass to bio oil, then biosar. The opposite picture is found when we see the oxygen content. In the biomass, the oxygen content is highest, whereas it is somewhat lower in the bio oil, that is the liquid product, and it is lowest in the solid product. So based on that, actually, this influences the heating value of the sample. Because if we see the heating value, that is the calorific value, that the calorific value of the biomass is relatively lowest than its products. So this is because of lower amount of oxygen and higher amount of oxygen and lower amount of carbon. Similarly, highest calorific value is found in the biosar. So this is basically for lower value of oxygen and higher value of carbon. So this is how the same kind of trend is found for other products as well. Now, based on this carbon, hydrogen, oxygen, and nitrogen, particularly carbon, hydrogen, oxygen, one can develop the empirical formula like this. These are basically, it is very simple. These are basically formulated using its atomic number. For example, this for carbon, the percentage of carbon content in this sample is 70 or maybe around 71%. So it can be divided by its atomic mass, such as 12. Similarly, for hydrogen, this is 3.99, so it can be divided by 1, which is the atomic mass. Similarly, for oxygen, also we can divide by its atomic number. Then after that, whatever the lowest value will be there, by this lowest value, we can again divide to all the values. And this is how finally this kind of empirical formula can be obtained. So one can develop this kind of empirical formula from the elemental analysis. For the other biomass and its products also, we can develop this way the various empirical formula and also the calorific value. So these calorific values are basically obtained from using that automatic bomb calorimeter. But one can use the Dulong formula as well. And in that case, some difference may be there, but the difference should not be very much or very large. So this is another properties of the sample. It is a combined sample basically between this bamboo and coal. So where bamboo is a biomass, but the coal is a petroleum fuel. And in that case, if we see the difference with the help of proximate analysis and ultimate analysis, say ash content, if we see the ash content is comparatively lower in biomass as compared to the fossil fuel. Similarly, the volatile matter is very high in the biomass, and because of that, the biomass can be converted into liquid fuel, whereas this coal cannot be converted because its volatile matter is very low. And if we go to the ultimate analysis, and if we see the carbon content is somewhat lower than the biomass. Carbon content is somewhat lower than the coal carbon content. And because of this, the calorific value of biomass is quite lower than the petroleum fuel such as coal. And the opposite trend we can see in the oxygen content as well. The oxygen content is somewhat higher in the case of biomass as compared to the petroleum fuel. So this is how it affects the properties in the ultimately in the properties between these two types of samples. So atomic ratios, generally we understand from the atomic ratio as the H/C and O/C ratio, and one can plot this kind of atomic ratio for different types of samples. For example, in the first diagram, we have plotted the atomic ratio of different types of biomasses in the H/C ratio versus O/C ratio in the form of Venn equivalent diagram. Whereas in the second diagram, we can see that these are the H/C ratio for different biomasses and their different products. In y-axis, we have plotted the H/C ratio, and x-axis we have plotted the O/C ratio. And these atomic ratios are also measured using the atomic number. For example, we know the atomic number of hydrogen, atomic number of carbon, and also we have estimated the elemental percentages of hydrogen, carbon, oxygen, etc. And based on this elemental content, we can divide both in the numerator and denominator by its atomic mass. Then we can get the atomic ratio such as H/C and O/C. So in this picture, if we see indicated by the blue color, so this is basically the products of biomasses, solid products of biomasses, that is the biosar for different types of biomasses. For example, the one is indicating the biomass as bell cell, but this is the biosar actually obtained from the bell cell. Similarly, 2 is the biosar obtained from the areca tree dust, and so on and so forth. So here, this biosar atomic ratios, both the atomic ratios are quite lower as compared to the other products. So this indicates that in the biosar, the carbon content is very, very high, and that's why its atomic ratios is coming lower as compared to the other. Similarly, if we see this color, purple color for bio-oil for different types of biomasses, so this actually takes the position in between the biosar and the biomass, because in bio-oil we have seen from the result of ultimate analysis that carbon content is somewhat higher than the biomass, but somewhat lower than the biosar. So that's why this atomic ratios also comes within this range in between these two materials. Then this red color is showing the biomasses. So in the biomasses, because of its lower carbon content, its H/C ratio value and O/C ratio value is coming higher than other than its products. So this is how one can understand by just looking this kind of Venn prevalent diagram of atomic ratio, that and have an idea about the elemental composition or elemental content of the samples. Now, TGA, DTA, and DSC. So these are the thermal analysis where TGA stands for thermogravimetric analysis. So this TGA basically used to see the thermal degradation with respect to the temperature. And DTA, basically the differential thermogravimetric analysis, which is given by dW by dt. And this DTA profile basically gives us the indication, or gives us the information, the rate of decomposition. So this type of two analysis can be done using a single analyzer called a TZ analyzer. And this DSC, basically the differential scanning calorimetry. So this kind of analysis or this kind of apparatus can be used to determine the heat flow or enthalpy associated with any kind of pyrolysis process, or the heat requirement in a particular pyrolysis process. Let us see some profiles obtained for this TZ and DTA and DSC diagrams. So here I have just taken two samples. For example, this bell cell and bell cell biosar. So the first figure is the bell cell, that is the biosar. This dark line is representing the TJ profile, whereas the dotted line is representing the DTA profile. From the TCA profile, that is the dark line, we can see that if the temperature here, we can see that the temperature is from normally 0 degree to 600 degrees Celsius. We can see that it has decomposed and it has come down from 100% to about around 25%. So we can see that 75% of the biomass has degraded. So this line is showing the degradation of the mass of the biomass or degradation of the web. So from that we can understand that within a temperature range of 600 degrees Celsius, we can get a 75% of the decomposition of the biomass. And if we use this DTA profile that at around 250 or 59, yes, 59 degrees Celsius, the highest rate of degradation is found. So basically this, as I said, the DTA profile basically gives the information of rate of decomposition, that is dW by dt. And also some more information can be obtained from this kind of TCA plot that up to 100 or maybe somewhat more than 100 degrees Celsius, there is a small decrease of this curve. So this indicates the moisture removal activity. So because of this moisture removal, its mass has decreased down, and after that, maybe after 200 degrees Celsius up to maybe 350 degrees Celsius, this is basically the pyrolysis process where we can see the decomposition of cellulose and hemicellulose. And after that, we can see the decomposition of some other products or elements, something like lignin content. And if we look about the TCA plot for the biosart, which is the solid product of the biomass of this kind of biomass, that is bale cell dust. So here we can see that this TCA curve has come down from 100% to only maybe up to 78% only. So we can see that it has decreased, the mass of the biomass has decreased only about 25% or something like around 25% only. So from this we can understand that in the biosar, since the biosar is composed mostly by lignin and less by cellulose and hemicellulose, so its degradation is very low. And also we can see with the help of this DTC curve that around maybe beyond 400 degrees Celsius only, its rate of decomposition is very, very high or highest. So this is how we can understand that how this biomass or its products, solid products, degraded with respect to the temperature. And also we can find out the rate of decomposition. Another product or obtained from TTSD, that is TEQIP III sawdust. So this figure is for the biomass and this figure is for the biosar. Here also we see the same kind of trend. We can see that 75% of the weight is degraded because of this heating up to 600 degrees Celsius, and maximum rate of heating is found around 288 degrees Celsius. Whereas in the biosar, we can see that up to 300 degrees Celsius, there is no decomposition because here the moisture content is also very less, and cellulose and hemicellulose content is also very less. So its decomposition is very low, up to 300 degrees Celsius. After that only decomposition mainly starts, and this occurs because of the decomposition of the lignin. Because we know that the lignin contents are very prominent in the biosar. So in that temperature range such as 350 or 356 degrees Celsius, the highest rate of decomposition is found. So another experiment or another kind of analysis can be done using this TCA and DTA profile. Basically, based on the TCA profile, we can these TCA profiles and DTA profile are for some other kind of biomasses that we used for another experiment. So this TGA profile is for this rain tree seed, and similarly this TGA profile is for cotton seed, and this is for yamine tree sawdust. So here the same kind of trend we get, but we will do some other kind of analysis here. That is the estimation of kinetic parameters. So for that, we can divide this TGA profile into two zones. For example, the first zone in between some temperature, something like 150 up to 250 degrees Celsius, and the second zone maybe from 250 to maybe 400 and something more than 400 degrees Celsius. Similarly, for other samples as well, we can we have divided we have classified into two zones, so that we can clearly identify or clearly estimate the kinetic parameters in these two zones. For evaluation of the kinetic parameters using these TGA profiles or TGA diagrams, we can take the help of this Coach and Fern method. This is very popular method for the evaluation of kinetic parameters. In this method, we can see that this kind of equation can be used. This is alpha AS, this is the reactant actually, and this alpha is the fraction of decomposition for this element AS, and we can see that BS and CZ are the solid and gaseous products. So this is the basically the reaction that takes place in this kind of method. And if we see that in the red form, we can write this equation, and that d alpha by dt in the differential form. So where it is, this alpha is the fraction of decomposition, and k is the rate constant, and this n is the order of reaction. And again, this k can be given by this equation, which is very popularly known as the Arrhenius equation, where this k is equal to a exponential of minus e divided by RT, where a is the pre-exponential factor, which is also known as frequency factor, and E is the activation energy of the reaction, and R is the gas constant, and T is the absolute temperature. For linear heating rate, this alpha, that is the fraction of decomposition, can be given by this simple relation, this m naught minus m divided by m naught minus m infinity, where m naught and m infinity are the mass of the biomass at the initial and the final condition, and this m is the mass at a particular temperature. Also, this alpha can be given by as a form of heating rate, that is d capital T by d small t. Now, this equation number 1 and 2 can be written in this form by using this integration of this fraction of decomposition from 0 to infinity, and finally this rearranging, because this is very actually somewhat complicated relation where exact solution cannot be found easily. So by substituting and rearranging, we can get finally this kind of equation. In the left hand side, it's a logarithmic function. In the right hand side also, we can get a logarithmic function, and in this equation, this portion particularly, that is 1 minus 2 RT divided by E, that is the activation energy. So this part can be considered as a sensibly constant, because for most of the values over a range of temperature, this particular value is found to be sensibly constant. And when we use the reaction order, that is n equal to 1, and if we take the logarithm in both the sides, then we can have a relation like this, which is given by the equation number 5. And now we can have some plots in the y versus x. In the y-axis, we can plot the left-hand side of the equation number, say 4 or 5, and in the x-axis, we can put the value like 1 by t. Since this part will be like constant, so in this kind of profile or in this kind of plot, we will have a slope which will be given by E by R. So this relation is when the order of reaction is other than 1, and if the order of reaction is 1, then simply we can use this equation number 5, where this y will be the left hand side of the equation, and x will be again 1 by t. So using this y and x values, if we make some plots for the two zones, that is the first zone and the second zone, for different values of reaction order, then we have a different types of this kind of plots. And finally, what we do, we use the best regression fit line, and this best regression fit line, say for example, is found for the reaction order. Say in this case, for the first zone, it is found for n equal to 1.8, and we can show it by the dotted line. And normally we get this kind of straight line, so for both the first zone and second zone. And if using the graphical method, if we can find out the slope of this kind of straight line for the best linear fit line, where n is equal to for different values of n, then by estimating the slope of this line, we can have, or we can determine the activation energy, that is E, because this slope is given by E by R only. So this is how we can find out the kinetic parameters such as the activation energy by estimating the slope of this curve, and also the pre-exponential factor, that is actually A, or the frequency factor. So that can be obtained by this baseline only whenever it intercepts with the y-axis, and by estimating the interception point, we can estimate the value of A, that is the frequency factor. So this is how for the 3 samples we estimated the kinetic parameters for 2 zones. For example, say rain-tree seed, in the first zone we got the activation energy something like 99.21 kilojoule per mole, and for the second zone is 104, and similarly for the other biomasses as well. Also, we obtained the pre-exponential factor, that is A, for both the zones in all the samples, and all these are found for the reaction or different reaction order, because the for different reaction in all the cases, the best fit line was found for different reaction order value. Say for example, in the first zone of rain-tree seed, we got the best fit line for reaction order 1.8. For the second zone, it was 2.2, and so on and so forth. Apart from this method, some other methods are also available to estimate the kinetic parameters, such as Agrawal and Subramaniam, and also the Friedman method. So here also we can get this kind of equation, and we can plot y versus x profiles, where the y will be the left hand side of the equation, and x in the x-axis it will be the 1 by t, and in both the cases also we get the slope by E by R, and thus getting the value of slope by a graphical method, we can estimate the kinetic parameters like E, or activation energy. Similarly, the A as well. So one can compare all these 3 methods for different types of biomasses, and can analyze a lot of things. So this is the DSC curves. In this, using this curve, we generally see the heat requirement for a sample in the pyrolysis process. So in this DSC curves, the heat requirement can be calculated using this very simple relation or simple expression. That is the heat requirement if it is Q. So this will be given by two terms. The first term will be the heat requirement, that is MB Cp into Tr minus Ti, where Ti is the initial temperature, Tr is the temperature at the temperature where the pyrolysis starts, and Cp is the specific heat, and Mb is the mass of the biomass. So this expression or this term will indicates the amount of heat requirement to heat the sample up to the pyrolysis temperature only. And the second term, this is Mb into delta HR. So this indicates the heat requirement for the pyrolysis itself. So here the enthalpy terms involves, and therefore sometimes we also call that the DSC curve the enthalpy requirement curve as well. Then in the red form we can write this equation in this modified form, this dq by dt like this, where this Mb is the mass of the biomass during the experiment, and when we integrate for different time periods and divide in both the side by initial mass of the sample, biomass sample, then we can estimate, or we can determine the heat requirement in this process. So this kind of this is the DSC, and these are the plots obtained from the DSC actually machine, and we can see that. Am I audible, Prasanna sir?
Yes. Good. Carry on.
Okay. It was disconnected actually. Okay. So this figure is for Bell cell biomass. So here we can see one endothermic peak here, and based on this peak we can find out in this portion how much heat actually was required. Similarly, in another portion, another peak we can see, endothermic peak we can see, although these are very small, because maybe the heat requirement was very smaller. So from this peak we can estimate, or this estimation is actually given by the software itself. Also we can verify with this equation. And another sample we took for the Erega tree dust, and here also we found some very small peak around here to show the endothermic heat, and very small peak was found here. And in the kg form we can see how much heat actually required in the different temperature range that is obtained from the DSC plots. For example, if for this sample, say Bell cell dust, within the temperature range of 30 and 120 degrees Celsius, we obtained the that means energy content was energy requirement was around 157 kilojoule per kg, whereas in the temperature range 210 to up to about 275 degrees Celsius, the energy requirement was about 15.9 kilojoule per kg. Similarly, for Erega tree dust sample as well, within this temperature range of 30 and 80 degree, it was the heat requirement was 3.186. Similarly, the temperature range of 200 to 250, the very small energy requirement was there. So this is how the energy requirement can be estimated using these DSC curves, and it is quite actually essential, because based on the heat requirement in a sample or in a particular process, actually influence to design the reactor, types of the reactor used for a particular process or for a particular biomass. Now look at the XRT analysis. So this is mainly used for to see the crystallinity or amorphous nature of the solid samples mainly. And for this purpose, analytical powder XRT is used. And as we know that in the XRT process, always we this law is a very popular law, that is Bragg's law is used, which is given by n lambda is equal to 2d sine theta, where is lambda is the wavelength and n is the order of the diffraction, and d is the spacing between two diffracted planes, and theta is the diffracted angles. So for the purpose of analysis, this Bragg's law can be rearranged to find out the despacing value we are using this relation. Apart from that, many researchers are using this EDX also. This is basically the energy dispersion X-ray analysis, where this kind of, obviously this is quite better than the XRD analysis, but the only thing is that in EDX is used only when we totally do not know about the any idea about the sample. But XRD, for the XRD, we must have some idea about the sample preliminary. But obviously, of course, we did not use this EDX in this work, so we will be limited, or will be covered only the XRD analysis of some samples. So these are some XRD spectra of biosar and its biomass. Say the first figure is indicating the biomass of TTSD. Here you can see that this this spectrum is not much very distinct. Some noises kind of peaks are found. So this kind of spectra basically indicates the amorphous kind of nature, although some local crystallinity is found. Also, at the peaks obtained at certain diffraction angle, or which is ultimately converted into despacing value in the unit of angstrom, some inorganic or some elements can be identified. For example, based on some peaks at different diffraction angle, that silica, that is SiO2, and this potassium ozonide, this KO3 kind of elements can be identified that to be present in this kind of biomasses. So as we know that this potassium ozonide is a very strong oxidizing agent. And similarly, if we see the XRD spectrum of the biosar obtained from this TTSD biomass, then here again we do not have any crystallinity nature. So this is basically the amorphous kind of nature, and also based on some peaks obtained at different despacing value or different Brake's angle, we can identify some elements, something like calcite, which is very much useful for the soil improvement purpose if we apply to the agricultural purpose, like on the soil, because it helps the soil remediation, or it can stabilize the soil, and something like this. Similarly, another element, that is K2CO3 kind of element, can be identified from this kind of XRD spectra, which is basically the equivalent to activated carbon. As we know, the activated carbon again is very much helpful or useful for the agricultural purpose. In most of the works, we see that activated carbons are artificially done in the biosar. But here we can see that this kind of, if we see, or if we get this kind of elements on the biosar, so it automatically have the property of the equivalent property of the activated carbon. So this is how some advantages we can get if we do the proper characterization with the help of this XRD analysis. Then this is another biomass like rice husk, and this is what a rice husk biosar. And in this XRD spectrum of this biomass, we again see some amorphous kind of nature, but some local crystallinity, which are basically because of the cellulose content in the biomass. Again, if we see in the biosar, because of this nature, very this kind of amorphous nature, this we can see that there is no crystallinity. Where some crystallinity nature was obtained in the biosar, but then the biosar, the crystallinity is not totally deteriorates. But based on some peak at certain Brake's angle, we can identify the graphite-like elements and silica type of elements, and we can see that both this graphite and silica are very much useful for the agricultural purpose. For like this graphite is very much as a soil conditioner element, And silica is, we know that this is very much useful for the plant growth, and also it enhanced the photosynthesis process of the plants. So for another types of biomasses, we can see this kind of XRD spectra, and using this XRD spectra, we can use another kind of analysis. That means determination of crystallinity index can be done using this kind of XRD analysis. So with the help of once we know the crystallinity index of a particular biomass, that we can have an idea about how much the crystallinity is there in the sample. So the crystallinity index can be determined using this very simple relation, but of course, some material, deep material science knowledge must be there. That is, CR is given by the intensity at the Miller indices plant, is 002 minus intensity of the amorphous plant divided by again I intensity at the 002 plant. So this intensity at 002 plant is basically for the crystallinity obtained at a particular, for example, in this figure, suppose if crystallinity is found, say, at 23° Braggs angle, and at this crystallinity and at 002 Miller indices, we can identify the intensity, and at the same time, for this sample, if we know the intensity at the amorphous plants, then using this relation we can find out the crystallinity index. So this is how, for all these three samples, we estimated the crystallinity index. Like for this rain tree seeds, we got the crystallinity index as 23%. For cotton wood, it was 21%. Similarly, in this case, it was highest. That means for elementary sodas, it was highest crystallinity was found, that is 28%. So this is how different types of analysis can be performed using this XRD spectrum. Now come to this another analysis, so, which is very useful for doing the chemical analysis. Basically, here or from this kind of analysis, we can get lots of information about the chemical compounds present in the in the sample, whether it is solid sample or liquid sample. So this is the Fourier transform infrared. So in this analysis, the mechanism is basically that the mathematical Fourier transform is used to convert the raw data into the spectrum, actual spectrum of the sample. So in the machine itself, the infrared is passed through the sample, and out of this passing infrared, some of the infrared is absorbed and some of the infrared is transmitted. And what based on this transmission and absorption, it creates a molecular fingerprint on the sample, and which is recorded by the machine. So based on this FTIR spectrum, lots of information can be obtained about the presence of the chemical compounds based on their functional group. So in the FTIR spectra, generally in the y-axis we plot the percentage of the transmittance, that is the percentage transmittance, and the x-axis the wave number is placed, as can be seen in this slide. This is the FTIR spectra for a sample, that is rice husk, both the biomass and its products, liquid product and solid products. So here you can see this is the FTIR spectra of the biomass of the rice husk. Say we find a very sharp peak in this area, that means in this wave number area, that is about 3,400. And from our literature survey, we can understand that we can know that whenever some peaks are found in this wave number, so it gives an idea of presence of hydroxyl group, such as phenolic or maybe alcohol. Similarly, carbonyl kind of group can be found whenever the peak is found around within 1640 or 50, something like this. Similarly, some alcoholic kind of functional group are also found by getting a peak in this area. So this is about the biomass. But when this biomass is converted into products such as the liquid products, and if we do the FTR analysis, then we can see some different types of properties. Say here also, of course, we get one peak, but this peak is not that much observed. So obviously, so that means we can understand that in the liquid sample also hydroxyl kind of group is there, which indicates the presence of alcohol and phenolic group, but it is somewhat lower than the biomass sample. So this indicates that during the pyrolysis to the liquid product, when it is converted to liquid product, some oxygenated compound actually is converted into some other kind of compounds, maybe carboxylated compounds. Similarly, the peaks obtained at around 1600 wave number. So this indicates the presence of carboxylic acid in the bio oil or bio liquid, because this is a liquid product. And we can understand, or we know that this carboxylic acid is basically under a carbonyl group, compound of carbonyl group, and this is obtained by the breakdown of the fatty acid. So which is a very common and useful elements of the bio oil. And if we look about the solid product such as the biosar obtained from this rice husk biomass, we get some peaks around this 3400, similar to this, but again this its intensity is quite lower in comparison to this biomass peak, and obviously it indicates the presence of hydroxyl group. Also, the peaks found at 2900 indicates the presence of aliphatic group, and most importantly, in the biosar, if we see that the peaks found at around 1600 and 1456, so this kind of peaks indicates the presence of aromatic compound, which is very important, because if we get some aromatic compound in the biosar, and if we apply this kind of biosar for the agricultural purpose, like improvement of the soils, and that will be very useful, because this aromatic carbon kind of compound stabilizes the soil composition. These are the FTR spectra for another sample along with its products, liquid and solid products. So here also we find some hydroxyl group of compound by this kind of peak in this area. And if we look about the liquid product, similarly we get some compounds or functional group of compounds like carboxylic acid, esters, alcohol, and all. Then again, for the solid samples, if we look, that aromatic kind of compound is very important, because we should be concentrated on this aromatic kind of compound, which should be there in the biomass if we apply this for the agricultural purpose. So here we can see that CC kind of C double bond kind of ring is found. So this basically indicates the presence of some aromatic kind of compounds like benzene, toluene, maybe something like this. So this is how lots of chemical analysis can be done with the help of this FTR analysis of the products of the biomass along with its raw biomass. Now, this is another type of analysis, which is called the morphology study. That is, we can study the nature of the surface of the biomass as well as its solid products, such as biosar. So based on this study, we can basically get some images from the very high resolution machine. It's called ASSAM, it is scanning electron microscope. So with the help of these images, we can see that on the surface, whether the surface is porous, or on the surface if some other kind of elements are present or not. So this kind of study can be done. So along with this ASSAM, the morphology study again can be verified with the help of this bed machine. This bed machine is also very popular for the morphology study, which full form is the Brunner Emmett-Taylor machine. And this basically used a mechanism of absorption and desorption of gas molecules such as nitrogen on the solid samples. And in fact, this kind of nitrogen gas is used in the machine itself. And a very popular method or very popular model known as the BZH, this is Barrett, Joyner, and Helenda model, is used in this kind of analysis or in this kind of machine. So now, what kind of information we can get from this bed analysis? Basically, we get the specific surface area of the surface of the sample, then the total surface area, pore size, if some pores are present in the sample, and yeah, obviously we can then verify this kind of result with the result or with the images obtained from the ASSAM. Also, some researchers are using this TEM analysis. This is another actually analysis. This TEM is the transmission electron microscope. But basically, this kind of analysis is used for, or this kind of device is used for the analysis of biological science, nanotechnology, or materials, and of course, material science also, to find out the grain size, pore size, etc. But we are not using this machine in this work as of now. So these are the various images that have been obtained from the ASSAM analysis at different magnification. So this is the images obtained for the Erica tree dust biosar. This image is at very lower magnification, such as 50 times, and this is somewhat higher magnification, like 500 times, and this is, and again some higher magnification, like 1,500 times magnification. So if this is how we keep on increasing the magnification, then we can get some or we can observe some pores on the surface of this sample. But these pores are very, very small because this size is in the micro level. So we have seen here one micropore, it is 2.53 micrometer. And again, we can see some more pores if we increase the magnification in the images. So this is how we can see that some micropores are obtained on the surface of this Erica tree dust biomass. However, at the low magnification, we did not see any kind of pores. So therefore, it is important to see at different higher resolution or higher magnification. Also, some fibrillar kind of structures are obtained or observed on the surface of this kind of biomass, so which actually gives the information about the presence of somewhat amount of cellulose. Although this cellulose is not much evident on this sample. Now this is for the biomass. Now if we see its products, so this is the solid product of this Erica tree dust biomass, that is the biosar. So here also we can see at different magnification, from lower magnification 50 times to up to 2,500 magnification. At lower magnification, no significant properties were observed, but at the higher magnification, we can see that some very smaller size of pores are found. It's about 1.87 micrometer. So if we compare this size of micropores between the biomass and the biosar, that this size of the micropores has reduced. So this is because of the process of pyrolysis, because in the process of pyrolysis, due to tar production and because of this clogging of this tar, sometimes the size of the pores may reduces. So this is why this is another very important analysis can be done with the help of this ASSAM, that if we keep on increasing the pyrolysis temperature, then what happens, this clogging of the tar on these pores increases, and thus the size of the pores reduces relatively as compared to the lower temperature or the biomasses. So this is another ASSAM images for both biomasses and biosar of rice husk. This rice husk is on the magnification of 2500 times. In this magnification, we can see some tiny white particles on the surface of the biomass sample, and we can conclude that because of this tiny presence of these tiny particles, that there is a coalescence of calcium and potassium kind of elements over the surface. Similarly, if we look at the biosar images at the magnification of around 2500, that we have not seen any kind of pores over it, but some flat surfaces we have observed with the agglomeration of crystalline and amorphous carbon. So because of this agglomeration, we can understand that there is a crystalline or amorphous kind of carbon is present on the surface of the sample. Similarly, this is another ASSAM images for bale cell dust biomass. Here again, we have not seen any kind of significant pore, but we have seen some raw corn kind of images, which actually indicates or gives an possibility of being the biomass as a hard kind of biomasses. But when we look at the biosar samples, the images on the biosar samples, at the magnification of 2500 times, we have seen some fibrous kind of species over it, and this also basically responsible for the presence of the cellulose, because although this is SAR particles or biosar, so in the biosar we know that cellulose percentage is less, but sometimes some cellulose may be present with a lower percentage, so this can be the indication of that. And if we see at a very high resolution, such as 5500, so here we can observe some pores of very smaller size, for example, like 0.54 micrometer or maybe 0.83 micrometer and something like this. So this is how at a very high resolution we can see some porosity on the surface of the bale cell biosar. Because this porosity has a very significant role if we apply for some kind of agricultural purpose, because if there is a pore, then it may be very useful for the agricultural purpose, because it can absorb the water and all. So this is how we can do this kind of various analysis with the help of this ASSAM images. Now, whenever we talk about the BET study, that is Brunner Emmet Teller machine. So since this machine is basically based on the adsorption and desorption of gases on the surface of the sample, and based on this we can see whether there is some porosity on the surface or not. So this can be seen by using these two kinds of isotherms. When these isotherms are plotted in the y-axis, the volume at the standard temperature and pressure, and in the x-axis, sorry, if we plot the relative pressure, that is P by P naught. So where this P is the equilibrium pressure and the P naught is the saturation pressure of the absorbent, then at the lower relative pressure, we have seen that desorption curve is somewhat higher than the adsorption curves. So this indicates that there may be some porosity on the surface of the biosar, because desorption basically responsible for the generation of the porosity on the surface. So this is how some kind of analysis can be done with the help of this BET analysis. Also, this BET analysis gives the idea or the size of the pores, what kind of pores are there and what is the size of the pores, and this can be verified with the images obtained from the ASSAM analysis. So this is how we can do some verification kind of analysis using these two kinds of morphological study. So another study which is again used for the study of chemical compounds present in the biosar or biomass, or maybe in the liquids sample. So this is a coupled device basically. This is GC stands for gas chromatography and MS stands for mass spectroscopy. In GC, what happens? The organic mixer is split into its individual components, and it is allowed to pass through a capillary controlled capillary column. And depending on this retention time on the or inside the column, with the help of this MS study, we can identify the amount of contents of that particular compounds. So this coupled GCMS instrument is very much strong and useful for analyzing the different types of compounds that is present on the sample. Particularly, we did some experiment for liquid products, that is the bio-oil product obtained from bell cell dust. So this is basically the GCMS spectra for pyrolytic oil obtained from the bell cell dust. So this kind of spectra are found the GCMS plot. So in the y-axis we see the percentage of abundance, and in this kind of spectra we see the written this at various times the peaks observed, at also the intensity of the peaks, that means the abundance of the peaks, and based on these peaks the software itself gives us the different compounds present in the sample along with its molecular mass and its molecular formula. So we can see the various compounds that have been obtained from this type of GCMS spectra. So lots of this kind of compounds can be seen, that is on this kind of pyrolytic oil, because as we know that the pyrolytic oil actually is very complex complex kind of substance. It contains lots of chemical compounds, and some of these are obviously of course toxic and poisonous also. So therefore this GCMS analysis is very important to see whether what kind of actually the poisonous components are present there or not, and what kind of aromatic compounds are there or not. Because although this pyrolytic oil as of now based on this composition cannot be used as a fuel, but it can be used for some other kind of purposes. Say for example production of some that may be some polymer like purposes. So for that to know about the details about the compound is very essential. Very briefly, if we see that lots of acid compounds are found in this sample, and obviously we know that the liquid products obtained from any kind of lignocellulosic biomass, it gives lots of acid contents. Also, we can see some phenolic kind of contents, phenolic kind of compounds with combination of some other types of compounds. And we can also see that this is a very useful device, that because it gives us the molecular weight as well, along with its formula of the compounds which are available or which are present in that particular sample. So this is another GCMS sample, and we can see this from this GCMS spectra and peaks obtained at different time, that and based on this size of the peak or the area under this peak, we can also find out the percentage of content of a particular compound in the sample. For example, if we see the compound based on this GCMS spectra, this kind of compounds are found, and also we can see the relative mass content based on this, based on the area under the peaks. And yes, yeah, relative mass content as well as the molecular mass and formula can be obtained from this kind of GCMS plot. And all these things are basically automatically found based on retention time. So one can identify the different types of molecules or compounds that is which are present on a particular liquid product obtained from the pyrolysis process. Now, these are very simple properties. These are simple physical properties, as we all know, but these are very important, in fact. So the evaluation of this kind of properties is very important, because the viscosity, for example, is a very important property for a liquid if it is used or if it is going to use for a fuel purpose. Similarly, the density and water content, because in the water content also, if we see that in the water content, if the water content is very high for a particular sample, then it will reduce the heating value of the sample. Similarly, if the viscosity is very high, it will plug the device, and so on and so forth. So we must know about the viscosity, density, and water content kind of properties, so that if these are not suitable, we have to, so that we can upgrade it for the further process. So for this evaluation of viscosity and density, a digital viscometer can be used. And nowadays, lots of sophisticated instruments are available to estimate this kind of properties. And for water content, a very common and very simple method, that is Dean and Stark method, can be used, which is basically based on the boiling point and the distillation method. So here we can see one Dean and Stark apparatus. It's a very simple apparatus. This is a boiling flux where we put the bio liquid or bio oil. It is a pyrolytic oil. And this kind of inclined side arm is used, which is connected with a condenser. And this boiling flux is heated, where this pyrolytic oil will be put up to the 50% of the flux, and for about 20 hours of time it will be boiled, and due to this boiling it will be evaporates, and again it will be condensed, and it will be collected over here, and then using this distillation process the water content can be separated. So another method is there, that is called Karl-Fischer titration. So using this method also one can separate the water content from the liquid sample, that is the bio-liquid sample. So for this purpose, nowadays different types of automatic Karl-Fischer titrators are available. So one can use this kind of titrator as well for this purpose. So here we can see some interesting results obtained from this kind of devices, like the viscosity. So if we see the viscosity, we know that viscosity of liquid changes with the temperature. But here, particularly the bioliquid, if we see that viscosity is increasing with the temperature, first of all, up to about 50 degrees Celsius. And thereafter, it again keeps on decreasing. So this happens basically because this is a just opposite trend, because we know that the increase of temperature, the viscosity of liquid always decreases. But here we can see that with the increase of temperature, the viscosity also increasing. So this happens basically due to the increase of temperature, the sample is dewatered, first of all. And because of this dewatering, that means loosening of the moisture content, the viscosity increases. But of course, it does not last long. So after 50 or 60 degrees Celsius, it again comes down. So this kind of trend is seen for all types of bio oils. And if we look about the water contents, these are the water contents present in different types of liquid. And similarly, the density of the pyrolytic oil can be seen from here. And of course, this trend of the variation of the density of the pyrolytic oil is quite very conventional. That is, with the increase of temperature, it always decreases. And also we can see that range of the density of pyrolytic is quite acceptable. Within, 1000 about 30 or 40 to 990 around. So within this only the density of the pyrolytic oil lies. So these are again some important properties that can be determined, or it is very important also. There is a flash point and fire point. So this kind of properties are quite required for characterizing the flammability of the sample, particularly the liquid samples. So for this purpose, we can use one open cup diesel tester. And using this tester, we can find out the flash point and fire point. The flash point is basically when we use some, or we try to ignite it, the flash starts. And the fire point is that the fire, generation of fire lasts for a period of time. That means for a few seconds or maybe for a minute of time. And generally it is found that fire point is about 10 degrees Celsius higher than the flash point. Now, if we see the pH value of the liquid samples, then a very simple digital pH meter can be used to find out the pH value for the liquid. And for the solid, because solid directly we cannot find out the pH value, but what we can do, we can mix this solid sample, and solid sample basically the biosar only. So this can be mixed with the deionized water in the ratio of 1:20. And we form a homogeneous suspension, and then we can estimate the pH value after a 1 hour or half an hour. So this is how we got some results from different types of bio-oil samples. Plus point, suppose for bell cell dust pyrolytic oil, we got the plus point is 88 degrees Celsius, whereas the fire point was 98 degrees Celsius. So this is about the difference is about 10 degrees Celsius. Similarly for other samples as well. Now, if we look about the pH value of the pyrolytic oil, these are quite acidic in nature because its value is quite lower than the this 7. So it is quite acidic, and of course that kind of nature we have obtained from the chemical analysis as well. Now, if we look about the pH value of the biosar, this is quite higher. It is from 8.3 to 9.3 about. So this indicates that the biosar, that is the solid sample obtained from the biomass, is quite basic in nature. And we know that the this kind of basic nature biosar is quite useful for the purpose of agricultural improvement or plant improvement. So another kind of characteristics can be done like a pour point, although we did not actually perform this kind of analysis. So this is basically the minimum temperature at which the liquid can flow. And one can see that pour point of most of the biowells lies in the range of -9 to -36 degrees Celsius. And in order to determine this kind of pour point value, one can use this ASTM standard like ASTM D97 or ASTM D5949 or something like this. So to get the flash point and fire point, one can use this kind of open cup digital tester. Once we use this kind of digital machine, this ASTM standard sometimes is not required, but whenever we do manually, then ASTM standard will be useful. Finally, this is my last slide, I think. We also perform one biodegradability analysis of the pyrolytic oil obtained from the bell cell dust. So for this purpose, this is totally a part of actually microbiology department. So we perform in collaboration of microbiology department. So here for this purpose, we consider two types of bacteria. That is the Pseudomonas aeruginosa and the Ectomobacter species. And we observed the growth of cell, dry biomass, and protein content of this bacteria with the in the mix when it is mixing with the pyrolytic oil. And we have seen that in the control environment, that is when there is it is not mixed with the pyrolytic oil, there is no changes or no growth of the these cells, but dry biomass and protein content. But we can see a very significant growth of the cells, dry biomass, and protein content at different time periods, say 24 hours, 48 hours, and 96 hours of culture. So based on this uh, observation, we used to observe the biodegradability with the help of these two bacteria for this pyrolytic liquid after 96 hours of incubation, and it is found that after 96 hours of incubation, mostly 20%, about 20% of the pyrolytic oil was biodegraded, whereas due to this ectomobacter species, it was about 18%. And due to this Pseudomonas aeruginosa bacteria, it was 20% biodegradation was found. So this is how we can also say that this kind of pyrolytic oil is quite biodegradability for the accidental kind of spillage situation. So this is how we can see this pyrolytic oil is quite biodegradable as well. So for all this analysis and experimental facility, I must acknowledge the Department of Mechanical Engineering, Tesbol University, Department of Energy, Department of Chemical Science, Department of Molecular Biology and Biotechnology, and Sophisticated Analytical Instrumentation Center, Tesbol University. So based on this work, I had some publications, journals and some books. And these are some conference proceedings that is obtained from this kind of work. And these are the various papers presented at different national and international conferences. Thank you.
Thank you, dear Monoj. It was a very lucid lecture. It was a lucid lecture and very interesting lecture. And I'm quite sure that the participants will be benefited from your lecture. Okay, now there are some queries that we can take. So,
okay.
Monoj. Okay, so yeah, from participants, we have got some queries.
Okay.
Okay, now here the first question is coming. Is there any process to make such type of final bioproduct, which has a low moisture content below 2%? It's been asked by Kumarji.
Yes. Yeah. I think that solid product that is obtained in the pyrolysis process, that is the biosar, in the biosar itself, the moisture content is very much low. If one look in my slides, I think it is near about 2% or maybe less than 2%.
Okay. Now another query from the Hitrius blocker. He has asked, sir, from your result of the different biomass, it is seen that the samples containing the high moisture content shows high value of volatile matter content. Thus, from this, can we say that moisture content helps the volatile matter content of the biomass sample?
No, that is not exactly, because moisture content, because this analysis were done based on the as received basis, because whenever it was received, and that way only it was analyzed. So therefore, the moisture content was somewhat higher than 10%, but it does not have any relation with the volatile matter, because the volatile matter is found by heating it up to 900 degrees Celsius. So there is no such relation. So this depends upon the composition, depends upon the cellulose and hemicellulose composition in the biomass, not because of the moisture content. Sir, you are muted, I think. Prasanto sir, muted. You are muted.
Hello.
Yes, you were muted.
Good, fine. Yeah. It is being asked by Pankaj Kalita. He has asked how to evaluate the pyrolysis temperature for determining the energy requirement through DSC curve. What is the range of condensing temperature for obtaining pyrolytic oil? The two questions actually he has asked.
Yeah, it is a very good question. DSC, that depends upon the facility available. generally DSC, whatever I have seen here, I have shown here that the temperature is up to, I think, 300 degrees Celsius. And yes, pyrolysis is not possible within the 300 degrees Celsius. But it is seen that if we see the literature, that there is no significant change of heat requirement after 300 degrees Celsius, because the main heat requirement is because of the increasing the temperature up to the pyrolytic temperature such as 200 or 300, from which the pyrolysis starts. So this is how we can, it is sufficient if we take the temperature for DSC analysis up to 300 degrees Celsius. And what was the second question? Sir, what was the second question?
Just what is the range of condensing temperature for obtaining pyrolytic oil?
Yes, range of condensing temperature, there is no such range, but yes, of course, there is some effect on the condensing temperature. As we performed the experiment, the condensing temperature was around the room temperature only. But yes, some researchers also do also use some ice and all, so that the condensing temperature comes below the room temperature, such as up to 2 degrees Celsius or 3 degrees Celsius, or maybe up to 0 degrees Celsius. So based on that, it influences the pyrolytic products, of course. But I directly now cannot say the range from this to this temperature, but there is some effect, obviously.
Okay. Then another question from Pankaj Kalita. Sir, I have unmuted you. Just unmute yourself. Yeah.
Yes, sir. Good evening, sir.
Oh,
good evening.
Good evening. Very good evening.
Okay. You ask your question, sir.
Yeah, thank you, sir. You have shared your lot of important data to research community. Thank you for that, Monoj, sir.
Thank you.
Sir, if possible, can you share your slides? Slide number 6, I want.
Slide number
6.
Okay. Let me.
6, no, sir. Pankaj.
Yes, sir.
Yeah, 6. No. Okay.
Yes.
Sir. Yeah, thank you. There's the same slide. This pyrolysis plant, no, sir? So
yes. This is the left one.
Yes, sir. Left one. The 13, the cylinder kind of things.
Yes,
this is nitrogen cylinder?
Nitrogen cylinder, yes, it's the nitrogen cylinder.
Yeah, sir. I have done one small experiment setup in my lab to extract energy from the waste plastics by using pyrolysis, actually.
Okay.
Initially, we could able to get some oil, but because of the less pressure or less heating value pyrolysis, we couldn't achieve that much yield. What may be the reason, sir? I don't have this exact setup. Like I don't have this.
Yes. So, yes. This is very. You are very right. If we in the raw form, if we see and if we investigate the what is called the calorific value, calorific value of pyrolytic oil is always lower, very much lower. But because of that, we cannot use it directly for our fuel purpose. So this is because of high oxygenated compound, as you can see from the elemental analysis or the different molecular analysis. Okay. But one thing can be done. Some blending kind of phenomenon can be done with the petroleum fuel, like diesel or petrol. So this much can be done. Otherwise, in the raw form, if we see that the calorific value is always lower in the pyrolytic liquid.
Yeah, one more question, sir. I think it is in slide number 17. That 259 degree, the optimum temperature, what you told. So in that range, that decomposition is very fast, no, sir? So can we keep the same temperature for entire process, so that we can get yield?
No. Yes. So yes. So this depends on the biomass. For other biomass, say this is the biomass of, this is bale cell dust biomass. So for this biomass, we found the highest heating rate at around 259 degrees Celsius. But for other biomass, it may not be so. maybe somewhat lower or maybe higher than that. So everything
how,
depends on the composition.
sir, how to measure these decompositions parallelly, because it is with respect to temperature, no? If you can see the slide, weight versus temperature.
Yes.
So yes, you are measuring the mass, or what? How exactly the decomposition is measured?
Mass. Obviously, this is mass. Manually, it cannot be done because this is done in the TGA machine only. TGA machine, thermogravimetric analysis machine only. So this machine actually gives you the raw data for both TGA and DTA plots, and using this raw data, you have to plot this type of curves. So manually, you cannot do that. Manually, you cannot measure this.
Okay, sir. Sir, thank you. The just last question is, like, if you can introduce a small experimental setup in a lab to the students, how much cost it may occur for this pyrolysis or any
Cost.
other? No,
you
for
are
lab.
talking about. Okay.
In lab, sir, in lab for students.
Yes, in the lab scale.
Yeah,
you mean lab scale? Yes, I had a lab setup. This cost is not much. I think within 1 lakh and all, I think you can make a very good small scale lab setup of the pyrolysis. Simply, it needs a reactor only, and a condenser, and this nitrogen cylinder, and the water supply and all. But you can improve, of course. You can do some more accessories you can add here. That means in the condensing temperature, you can reduce the condensing temperature by using some ice and all, something like that.
Sir, can I contact you for this help?
Yes, you can contact, but I think I will give my details to the coordinator.
Manoj.
Yes.
Manoj, can you could have given your email address, no, in the slide.
Okay.
No, later on you can also give the contact number. You can also give me the contact number. I can share with them.
So I will
share
give
with them.
I will give the coordinator, and also I may give to the this WhatsApp group as well. I think.
Okay. Yeah. So we have got
WhatsApp in the WhatsApp group.
We have got one WhatsApp group of the participants. We can share your details with them. Okay.
Thank you, sir.
Yeah. Okay. Mr. Dr. Venkatesh, thank you.
I can share the slides as well.
Okay. Definitely that is to be shared, because participants are asking for the slides. So we'll be giving the slides as well as the certificates together. Okay. Well, thank you, Manoj. Thank you.
Thank you.
It's a very lucid talk and very informative talk that you have delivered. Okay, it's a very nice work that you keep working like that. And I'm definite the participants they're mostly benefited and what the lecture that we have delivered today. Thank you. I convey my best regards and heart full of thanks.
Thank you, all the participants.
Okay, thank you. Okay, now it's over to Vidisha. Vidisha, are you here?
Yes, sir.
Yeah. Now we have got the the next program. Yeah.
Thank you, sir. Thank you, sir, for your valuable words. Now we have Dr. Vishwaranjan Phukon, sir, academic registrar of Assam Science and Technology University, and also TEQIP coordinator of the same university. So I would now like to request sir to give the concluding remarks. Over to you, sir. Sir, are you listening?
Sir, good evening, sir. Good evening, sir.
Good evening. So it's a nice program. In fact, this emerging technologies in biofuel production, and I especially congratulate Mr. Prasanto Chaudhary and Dr. Bharat Kakoti for successful organizing of this webinar. And speakers were also very relevant, are from very relevant, topic. This is the Dr. Rupam Kakoti. He is a professor in head of the department from the Tezpur University Energy Engineering Department, and another is Dr. Biplab Das. That was from mechanical engineering for NIT Silchar, and Dr. Pankaj Kalita, Assistant Professor, Department of Energy Engineering, IIT Guwahati, and I have just listened to Dr. Monoj Bardalai. It's a nice presentation, in fact. And I say thanks to all these resource persons, particularly for their time and the effort, particularly for, given for our student and the researcher, and the acceptance of requests from our coordinator. And thanks, and keep it up and be with us for our student and our researcher. And I would here like to say that the university try to encourage all the faculty member of each affiliated college as well as the researcher for the research and the work related to the academic development as a creation of a very good academic environment to help our student also. And university also develop one central research hub that we are trying to develop this hub as for the very we can say that the high-end research program. And for that, I welcome all the faculty of this Assam Science and Technology University is under this Assam Science and Technology University, all the students to join and take the best benefit out of it. Not only that, the other faculty, even other faculty, the outside of this Assam Science and Technology University, they can also join for their research, and then they should take the advantage of this research hub. And Dr. Bharat Kakoti, he himself is one of the looking after, he's a key person of one research hub. So with the help of Dr. Bharat Kakoti also, one can assess our at least one facility of part of the facility of our research hub. Then we have Mr. Monoj Bardalai. He's also looking after a part of the research hub, and Mr. Navajit Dev Chaudhuri. So student can contact these three persons, Bharat, Manoj, and Navajit, for the support from our research hub. And probably as a young university, we have very good facility, I think we should say. Then effort will continue. And my dear student, this is your life. So you'll have to take the best benefit out of the available, the resource you have. You be in contact with your teacher and make your own career great, and so the state as well as the country also. So this is my wish, and I congratulate all of you, and also thanks to the coordinator particularly for giving me the opportunity to speak at least few words with you. Thank you so much. And Vidisha also, Ms. Vidisha, you have given me this permission also. Thanks, Chaudhuri, Bharat, and Dr. Manoj. Thank you all.
Sir. Thank you, sir. Thank you so much. Thank you.
Thank you, sir. Thank you for your inspiring words. Now I request our participants to please give any feedback if they want to. They can raise their hand, so we will unmute it. Okay.
Hi. Good evening, ma'am. Good evening.
Yes, sir. Yes, sir. I'm
Good evening.
listening.
Can you?
Yes, sir. We are listening.
Yes. Dr.
Yeah,
Venkatesh, yes.
yeah. This is Dr. Venkatesh Ramani, Assistant Professor, Department of Mechanical Engineering, BMS College, Bangalore, ma'am. Let me take this opportunity to congratulate the Assam Engineering College, Department of Mechanical Engineering, and Assam Science and Technology University for organizing such a informative, fruitful talk to the audience in the field of this biofuel productions. Congratulations, sir.
Thank you. Thank you.
All the speakers from the day one, from yesterday, Rupam sir, Pankaj sir, and Das sir, as well as today Manoj sir, they have delivered the wonderful lecture on production and utilization of the biofuel in all aspects, in fact. So I also thank them for sharing their informative research. Thank you. Sir, one request from my side, this program is not sufficient for 2 days, in fact, because
Yes.
in future, if you are planning to conduct such a programs, please try to conduct by adding the final product of individual biomasses. Like if we can take biodiesels, so the whole process of different methods of extraction biodiesels, and finally how to take the policies required to bring into market to that biodiesel. In that sense, if it is ethanol productions, so all the raw materials, the manufacturing things for policies, government schemes and government encourages, so all these things please include in the future program, so it will be much helpful to create a Atma Nirbhar Bharat, sir. Thank you.
Okay, thank you, Dr. Venkatesh, for your kind words and the advice that you have given to us, and it will be taken care of for the next time. Actually, very limited time we have to make it, prepare the seminar, we prepare the webinar, so we couldn't include so much of things because it's so vast. It's such big field now. We can't consider that we can't accept the whole as a whole. But what you have suggested, that is very nice. Okay, so that we'll be thinking of for the next webinar that we are going to, and you'll be informed. They will be informed, definitely, sir. You'll be informed, and we are planning for that one. What you have just suggested. Okay, thank you. Any more from the participants? You raise your hand. We have with us Dr. Kamal Kumar Brahma.
Yes, sir.
Dr. Kamal Kumar Brahma is there.
So Mr. Ratnadeep Malakar has raised his hand.
Okay.
I have unmuted him.
Thank you. Okay. Then the Kamal Brahma will be going to him. Yeah. Ratnadeep.
Good evening, sir.
Okay.
Am I audible?
Yeah. Carry on. Yeah.
Good evening, sir, and good evening to everyone. I am Ratnadeep Malakar, a final year undergraduate student. So, this 2-day webinar series helped me a lot. Like I literally say that yes, I have gained a lot from it. Cause in my final year only, I am working on a biogas project. So this webinar, particularly Pankaj sir's session, was very helpful. The rest of the speakers were equivalently, like they have the knowledge I have gained through their sessions is like tremendous, and I'd like to thank all the coordinators. Special thanks to Mechanical Engineering Department of ASSAM Engineering College and ASTU for conducting the webinar. So thank you.
Okay, thank you so much. Then Dr. Kamal Kumar Brahma is there. Hello, Mr. Brahma.
Hello, Prachanda.
Yeah.
Good evening.
Yes, say something, sir. Say something.
It was very excellent. Management from management, excellent, and everything is okay.
Thank you.
From inauguration to this last Pukonchar speech, it is very nice. And as
Thank
well as
you.
this renewable energy,
Yeah.
actually wind energy is very important these days. So
Yes, yes, yes.
next, when you do a webinar, you may consider wind energy.
Yes, yes,
Very
yes. Thank
nice.
you.
Very nice person. Thank you.
Yeah, thank you, thank you. Thank you so much. Thank you so much.
Thank you, sir.
Any more? Any more? You can raise hand if you want to comment, live comment. Any student from AEC? Any student from AEC? Anyone from AEC? I think Apalak Sharma is there. Apalak Sharma. Apalak, are you there? I'm unmuting you. Apalak. Hello.
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 Hello. Am I
Hello.
audible?
Apalak.
Hello. Am I audible?
Yeah, yeah, yeah.
Sir, it was a nice program. It was a great learning for us because it's also new thing. We have learned many things. Only the thing is it was a 3 hour program, so it
Yeah,
stretches
yeah.
a lot. So if
Exactly.
the duration
Exactly.
was a bit
Mm-hmm.
it had
Exactly.
been more beneficial to us. That's the
Yes,
thing.
yes,
And
yes.
best the quality of session was really great, and we learned a lot of things, sir. Thank you, sir.
Okay, okay. Thank you. Thank you so much. Okay. Actually, that we need the advice from your side. Actually, that's why. So in a limited time, actually, we have to arrange. So that's why actually becoming so much of big. So next time it will be taken care of. So one lecture in one day. Okay, so that it can be easily digested. Okay. Then we have got the Anindita Mahanda from Assam Engineering College, I think mechanical department. Anindita Mahanta. Hello, Anindita Mahanta, can you hear me? Hello, Anindita Mahanta. Hello. We have the Bikram Kalita. Bikram Kalita. Bikram Kalita. Okay, I think they are not getting me. Debo Pratim Sharma is there. Debo Pratim Sharma. Debo Pratim Sharma. Hello. Debo Pratim Sharma. I think they are not getting me.
Yes.
Pranjal Sharma. Pranjal Sharma. Getting. Juktakhi Saigya. Okay.
Yes, sir.
Yeah, yeah. Say something about the course that you have attended,
Good
about the
evening, sir.
webinar. Yeah, good evening.
Good evening to everyone. Sir, it was
Yeah,
a nice program and we learned a lot of things.
okay. Thank you.
Sir.
And was it useful? Was it useful for your course? Hello, Juktaki. Hello, Juktaki. Okay, Pranjal is there. Pranjal Sharma. I think they are not being able to.
Yes, sir.
Yeah. Okay, Bidisa, there you carry on. Thank you for the live comment that you have commented on this topic on this webinar. That's very much thankful, and to the resource persons they have given the lectures these days, and thank you the audiences, and thank you all the participants. You have really played a big role. I am telling you. Now over to Bidisa.
Yes,
Now over
sir.
to Bidisa.
Yes, sir. Thank you so much. Now, with this, we have come almost to the end of our 2 days webinar on emerging technologies in biofuel production 2020. Now, I request our coordinator, sir, to give the vote of thanks and wind up the session.
Okay. Thanks. Hello.
Yes, sir, you're audible.
Thank you. Yeah. So thank you very much. First of all, I must thank the ASTU. It's a collaborative research scheme. So it was a part of the project under collaborative research scheme, jointly organized by the Mechanical Department, Assam Engineering College, and ASTU, Assam Science Technology University. So I must thank them. So I am always obliged to the VC sir, Dr. Dhiraj Bora. Then the principal of Assam Engineering College, Dr. Atul Bora. Then academic register, sir, and the TEQIP coordinator, Dr. Biswaranjan Pukan, sir, ASTU. Then the Ranjit Kumar Datta, sir, and not least but that I must take the mention his name. This is Dr. Bharat Kakoti of ASTU. He has helped me a lot. He's a co-coordinator. He has given me a lot of advice there. Then the core team, that was the support team, they have played a big role. They had a big role. I must thank them because they have worked day and night for this in a limited time because this webinar was arranged. So I must thank the Onimesh, this Sushanta is there, Samiran is there, Bidisha, she is taking a lot of effort in this regard. Then Neeraj Kashyap is there. Neeraj he is doing as a project assistant. He is doing the project under me in the ASTU. So they have done a very big job for this particular webinar to make it successful. So I'm always obliged to them. And sure, because I don't know how this because it was in a very short duration. This had to be arranged. So next time this will be taken care of what the participants, what the advice that you have given to us. So definitely, because it's at a stretch, this 3-hour program is really it's very tiresome. So it will be made. We are planning for the next webinar shortly if the time permits us. So that we are also looking for to make one arrangement for this another webinar when the one talk in a 1 day and 1 hour time, so that it can be easily digested. Okay, thank you all. Thank you. Please keep in touch, and your e-certificates along with that the webinar material will be shared, will be given either in the mail or in the WhatsApp group that you don't worry. So by next week you'll be getting everything. We'll keep in touch and also take our regards, also take our love, the heart full of love. Then you always keep in touch. We can do some in a collaborative way. We can do some next project even. You can consult with us. You can take our contact numbers. I can give all the contact numbers, email address of the resource persons so that you can make something new. And what Dr. Venkatesh just he has mentioned about the Atmanirbhar Bharat. So always to do some collaborative way so we can make the small things to be grouped together to make it big. Okay, so thank you very much. Thank you very much, sir. What the present, all these participants, along with all the organizing committee members present here. Thank you so much.